Ciao people! Hi! How are you? How are you? Welcome back. Nice to see you here. Thank you for coming. Hi, hello internet. How are you? Hope you are fine and that you have a video and everything. I will change to this other screen so you can have the document. So, how are you? Everything fine? I hear that Santa is coming to town. Well, should be little Jesus in here. Yeshicek is coming to town. Actually appearing, I'm not sure the magic of little Jesus. That is like unknown to me. But yeah, we don't have snow here in Prague. I'm not sure where you are, internet. I hope you have some snow and cold. So yeah, and you? How are you, people? Fine? Everything good? Yes? Okay, so we are going to start our class number 11, right? Yeah, lesson 11, manual and automatic detection of command and control channels. And you can see how we are being controlled by some channel. We are the kind of astronaut, we don't know. Thank you very much for the awesome drawing. The one where we automate all the things. Thank you very much for all the credits, and we have an extra credit that I'm not sure. Oh yeah, there you go. And part of the content is also thank you for Alea Goma. If you're there watching us, Alea, thank you very much. You are going to be using some tools thanks to her. You have all the links as always. And we are ready to go to the results from the survey. So we have 27 responses. Much more than 9. Thank you very much. It was okay, too fast, 15%, too slow for somebody. So maybe or rightish with a little bit too fast. So we will see about that today. As always, remember that the feedback is not only for the next class, but any other past class, but also for the future. We go through this for the preparation of next year, okay? So the more you can tell us, the better. And we have the Pioneer prizes for assignment number 1. Something we want to say about assignment number 9? No? Nothing? Okay, it's super hard because we want to say stuff. Huh? 8? 9? 8? Okay, the number we will check. But it's super hard because we cannot say details because some people are still playing. But at the end of the year, we are going to go through some of these ones so we can tell how to solve them, specifically also for the people on the internet. So we have as a third place a solderless zero dongle for Raspberry Pi 0 or 0W. And that prize goes to Lukasz Kampflu 1. B4M Lukashi. There you go. Happy hacking. And the second is going to be a USB 2 isolator. And I'm not sure. This is one that protects your device, right? It's like data. We are not sure. I forgot about this one. But looks very nice and have like stuff in the middle and everything. So this one goes to David Costadadva. Bravo, 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 bravo. Well done, well done. We should have at the end of the year like a top ranking of people because I see familiar faces from time to time here. Maybe they are selling them. I have no idea. Maybe there is a black market of devices here. And then we have a DF Robot Beetle Raspberry Pi 2040, nice chip, mini developing board. That's a beautiful thing with LEDs and USB-C. Oh my God, and so small these days. And the fair price goes to Tomasz Wesel 27. B4M Tomashi. Bravo. Well done, people. Well done. You're so lucky you're going there. They used to be coming to the middle to capture this one, right? Like, yeah, and I've done it very fast. So We have some parish notices, exam, and bonus announcements. The first one is that we finally settled the dates of the exam. So those are the officials. Take a note, please. January 21, January 23, and January the 30, and February the 6th. Only for CHEBEUT students, not for internet people, okay? Maybe for internet people we have a surprise. I don't know. We will see. But those are for you. Usually it works that you have to register. There is a limited amount of people per exam, so be sure that you register if you are coming. And also, yeah.
Just a note for this, it's not possible to register yet. They will be in course, I think, over Christmas or before Christmas it should be up. But those should be the dates. So if you have other classes and they might ask you for, hey, when would you like your exams? So we will have ours in those dates. So you can try to start planning a little bit.
And also we can say that, remember that you can take any of the exams. If you go to an exam and then you have, imagine, B, you approve, and that's fine. You can go home. You can come later if you want to improve your grade. And if the second time you have a worse grade, you keep the B, right? So you can B, and then if you are better, you have an A or whatever. Some people, they do that.
Also, you can come to the exam all the times, even if you have an A, because it's fun, right?
You can come and have 4 CTFs and have fun during hour on something. And then the bonus assignment, we decided the date is going to be open on December the 20th. At 9 p.m. If you remember, we're going to give you more details next class, but the bonus assignment is kind of a very relaxed, long-term, like 10 days that you can play a CTF like the exam in your own terms at home, and if you approve the bonus, you don't have to go to any of the exams. You just approve and bye-bye, okay? So I suggest that if you believe you have the time, take the bonus. If you don't approve, nothing happens. You can come to the exam. If you approve the bonus, then you don't have to take the exam, okay? More details later. Is it possible to get the same amount of points from exam that bonus? Repeating for the video, please be sure that I'm doing this because sometimes I'm not repeating. Yes, the amount of points is the same. Not exactly how the grade is computed because you have more time and stuff like that. And also, like, you have a different minimums, right? The amount of that you need to approve the exam is different from the amount you need for the bonus. But the number of points is the same, like 100. Perfect. So, class outline, manual detection of command and control channels in the network, traffic analysis with Zeek, automatic detection of command and control and attacks with machine learning, and sleeps IDS, okay? So, let's gonna start. Manual detection of command and control channels in the network. So our goal here is to learn how to detect these command and control channels in the network. Remember last class that we were saying what is a command and control? It's any channel that we are using to actually go and find whoever is controlling us and receiving the orders back, right? So receive an order, do this, and then we report. So any channel that we are using, it's going to be a command and control channel, from audio to pigeons to USB to whatever, okay? Oh yeah, and also I have like more mandos and other things for questions, only good questions. So think your questions, and if they're good enough, you can get the mando. So how are we doing this detection of command and controllers, and why do we care? Well, because malware and attacks can do many things. They can do scans, which actually a lot of administrators also do scans. They can do exfiltration of data to Dropbox, which actually looks like your Dropbox access. So one of the things that are very unique of malware is the command and control channel. So a lot of the detection focusing on, can we find those? If you can find these command and control channels, it's a very clear confirmation that there is malware. So confirmation is key. It's like, is this a new game or somebody's trying to infect me? And then you know if the malware is autonomous of control because you may see the commands. So you have an idea who is behind this. You know if the malware works or not, because if you see the command and control that is closed, the port is closed, the domain is not working, you might say, oh yeah, I'm infected, but it's not working. So relax a little bit. And finally, you will see if the malware is alive, which means it's sending commands right now to you, or if it's very old malware that is not sending anything more, okay? So that's why we want to do the detection of the command and control. However, this is very tough, people. We are going to be doing some analysis by hand. We are going to be doing some analysis with machine learning, but this is a very, very tough situation. Because if I give you command and control in a packet, you will see and you will say, oh yeah, for sure, this looks okay. But when I give you command and control in the middle of 20 million benign packets, it's going to be very tough, right? So this is the reality of the detection and the defense. So expertise is key, and the context here is critical. So let's detect some command and control. In this class, we introduce a new way of putting stuff in the document that is this, I don't know how to call them. Like pop-ups or drop-downs, so you know exactly in which Docker or computer you need to be for the following commands. This is because, especially in the Stratosphere Cyberlab, it's a little bit confusing. Where should I be executing this? So we are going to be trying to see if this methodology works out. This is for all of you, and is something you do in your host computer, not in any Docker, okay? So we need you to download this pickup file. You have here two links, Mega or Drive. Please download them to your computer. We are going to be using Wireshark. And if you also want to download from your Dockers in CVUT, you can do it from here, okay? So I'm going to give you some seconds for this until we can open Wireshark. And also it's in the Stratosphere Cyberlab in this data folder, okay? So I'll just give you something, download. You can open Wireshark on it. Latest. Shouldn't be so large. Ready? Okay, so let's gonna open Wireshark. You should see something like this. So these are all the packets that you can see happening, coming and going, and a lot of things. I'm just scrolling there, right? Go, 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 to have an idea. So, do you see how many packets do we have? 3,000. Where do you see it? Here in Wireshark? If you go bottom right, you see there packet 3,000, very fast. If not, you can count in TCP dump. So we have 3,000 packets. And the idea is to go through using a small methodology. So the methodology is the following. Usually, we want to analyze every packet and to be able to understand each packet and to be able to say what each packet is doing. It's very hard, especially if you have a couple million packets, but we are going to try. So the methodology is identify the connection, whatever is happening, benign, malicious, something, you check and say, oh yeah, if it's for us or not, and then you filter it out. And then maybe you colorize, we will see maybe colors conversations, sometimes yes, sometimes not. And then you continue until we identify all the communications, okay? This is the only way to be sure that you actually check every packet. Until you gain more and more experience analyzing, it's very hard to know what packets are doing, if they are benign or not, right? So as many things in life, practice is what you need to do this. So let's do the step-by-step analysis, okay? So before starting, we are going to be adding a new column in Wireshark. It's going to be the TCP stream. So if you go to Wireshark, we did it before. Remember, you go to the columns header or menu, right-click, and then you have here all the columns. You go to column preferences to add columns, and in column preferences, you press plus, and when you have a plus, you have here the new column. We are going to put here the name stream or something like that. The type is going to be custom. So you pick up and you say, hey, this is going to be custom. And then the specific field is going to be, like it says here, tcp.stream. Okay? tcp.stream is the field. And then you do it, you press enter. And then you can move it up a little bit. Just for me, after host, you can put it wherever you want. And then you press OK. So what is this new field? Well, this field is called the TCP stream and identifies all the packets that belong to the same connection or the same flow or the same stream for Wireshark. So you are sure that these packets with 0, they are all related. However, this one with 1, it's another connection. And then you have more zeros, and then 1s, and zeros, and stuff like that. And then you have 2s and others, okay? So this is going to help us a little bit identify, are these packets part of the same communication or not, right? Because they can be all overlap. So once we have this question, the column here, we are going to go to the first packet, this packet here, coming from the IP address 192.168.1.1, going to 192.168.196, port 22. Who knows what protocol is this? What are we looking at? SSH. Good or bad? Malicious? Benign? Are we infected? We don't know, right? Like, not enough information to answer your question. So we have some length. There is no information about the host because there is no hosting here. Encrypted packet. So far, what is 192.168.1.1? Usually, mostly, probably. Default gateway, right? We don't know, but usually, because of tradition, because of whatever, the first computer in the network usually is reserved for the gateway, the router, because you create the router. So it's kind of okay. The router is kind of connecting to some internal computer in SSH. Okay. Cool. We don't know what's going on, and you don't have enough information. In my mind, that would be a little bit suspicious. Why anybody from the router is connecting back to an internal computer? That should not be the case. However, because we did this capture in the laboratory, we know what's going on. And this is a way to actually access one of the computers to manage it. So we confirm that this is not related with any malware or any attack. But if this is a real-life capture that you find on the internet or you do yourself, then you should be aware of this one. How do we filter out this connection once that we know what it is? With this not TCP stream equals 0, okay? So you go here to the display filter, and then you add not TCP stream equals 0, and you press enter, and that's it. Now we have the rest of the packets, okay? We identify, we select, we clean, and we continue. So, second one, who can tell me what is the next one? Port, destination port, 80, usually reserved for web, HTTP, stuff like that. Does it say protocol HTTP? No, it says TCP. Why? Yes, exactly. So HTTP is application level. So why this here does not say HTTP in there? If 80 is reserved for mostly HTTP, why it only says TCP? First Mando. No? Nobody? Yes? So this packet goes to port 80 and creates all the headers up to TCP, but for reasons unknown, there is no application listening in that port, so it doesn't go up to the layer of application, doesn't go up to HTTP. So you don't have a header HTTP, only have header TCP. So remember that not all the packets go up to all the headers up to the application layer, right? You have some of them are acknowledged that are only TCP. So to confirm this, you can follow the TCP stream. Remember this from class number 2, I think? So right-click, follow TCP stream. Sorry for the zoom. I don't know how to tell Wireshark to make all the fonts bigger. So right-click, follow TCP stream, and then you're going to have this with the content that is empty because there is no content, right? And if you close that window, you will see all the packets related to stream number 1, and you can see that looks like an attempt. Like I want to go to 80, nothing back, 80, nothing back, 80, 80, 80, 80. There are no packets going back, so probably the port is filtered, okay? So Once we identify this and say, oh, well, okay, that's weird, but I cannot say that it's malicious. Maybe later you can check that IP if it's malicious according to the threat intelligence of the internet or not. Not what we can do right now in Wireshark. So let's filter it out. That means now we have no stream number 0 and no TCP stream number 1, okay? So you can go here and directly replace that by the new filter. And then we don't have TCP stream 0 or 2. Next one. What is the next packet? Sorry, I'm not sure if they hear you, Tomashi. Look at that, he's giving an opportunity. So, DNS, I know you know this one. I will go with that. Some of you are shy on here, but you are thinking, I know this one, and that's it. But maybe you can chat us what it is if you don't want to talk on the air. Yeah, that is a DNS request, and it's also going to the default gateway, which usually is also the DNS default DNS of computers in local networks, and it's trying to resolve the 0 Debian pool ntp.org, which looks okay, and it's a normal DNS resolution, nothing suspicious there. So what we are going to be doing is actually also blocking it out. But I don't want to forget all the DNS because it's a bad idea. I just want to forget all the queries that are related to ntp.org. So I'm going to say, hey, and the DNS query name should contain ntp.org. Okay? Everybody? Tell me if there are questions. If you have questions, the correct way of saying is stopping me and asking the questions. Internet questions? No? Okay, so now we don't have those anymore. We have other packets. What's the next one? What are those? Another Mando. Mando? Do you want to go home? Yes, yes, I want to go home. What is that? Synchronization? Actually, yeah. So what is NTP? Network time protocol, very well. That means that, yes, it's going to those computers on the internet and trying to ask something to get some time back. It's synchronizing the clocks and saying, hey, I want to know what time is on the internet, so this is the way every computer does it, okay? So that's going on in there. There you go. One by one, we are going to conquer Mandalore again, right? I go, 1, 2, 3. Whee! Look at that. And then we just forget all of this because this is not malicious. How do you know it's not malicious? Well, because NTP is a synchronization protocol. I'm going to the internet to ask, and there are few things that you can do attacking NTP. One is a DOS attack, which means sending thousands, millions of NTPCs, but this is not the case. We have like 20 and that's it, right? So the normal behavior of computers is actually to go to these NTPs and synchronize. And if you remember the DNS we just forgot like a minute ago, all those the DNS resolutions are related to those IPs. So those are the official actually NTP provided mostly by Debian, okay? These ones. So we go here and we just forget everything, right? Please do this in your computers, right? Be sure that we are doing everything again so you understand what's going on. Okay, next one. What's going on? What is that? Actually connected, very well. So you have here that we are connecting to some weird computer. If you remember, the same IP that we saw before, but now it's working for reasons unknown. And then we do a retransmission of the packets, and then we have a SYNAC. Like, oh, okay, so it's open. And if you pay attention to the protocol, still we're talking TCP level, right? LAC, SYN, SYNAC, ACK. And then finally, we can send data. So this goes up into the layer of HTTP, and this packet in particular has HTTP, okay? So what do? Right-click, follow, TCP stream or HTTP stream is the same. And now we have something. Let me see if I can make this bigger, bigger. Oh, yeah, there you go. So some fonts I can increase. So what can you tell me? Is it good? Is it bad? And what is an ELF? There is, sorry, I'm not repeating. There is an ELF file. So what is an ELF file? Executable uniform, very well. And that's good or bad? Why? Why is bad? But then it can be good. It can be also good. How do you know it's bad? That's a good answer. But from there, without accessing to the file, right? Why is this that's telling you that's bad? What are the things? Okay, suspicious is good, but this is good, right? What makes you suspicious? The fact that there is an ELF file? So for the ELF file, Mando, or I have a very weird Pokemon. I'm not sure, it's like a turtle. I don't know. It's a turtle. It's so much a turtle, right? Yeah. It has like a tail. I'm not sure. You should check. So Mando or turtle? Turtle. 1, 2, 3. Witcher. There you go. It's not Pikachu, so I don't know. So I would say that the first suspicious thing is that it's not encrypted. Right, we don't download unencrypted things from the, this is not the 90s, people, right? So stop doing that. No, we don't download encrypted anymore. That's very weird. And then we see that you're downloading a binary executable file unencrypted from the internet. That's suspicious as it gets, right? There are few reasons why to download this. You can do that by hand for sure. You can do this with some command, but this is not the usual behavior of a lot of computers. So if you know what's going on, I say, oh yeah, that's an administrator that is downloading a executable file, awesome. But if not, yeah, this goes suspicious very fast. So also I want to say that the name of the file is ntpd, right? That's the name that the file has, which would go to ntp daemon for some reason. And then you have the user agent, that is wget, automatic tool. And then you have not a lot of things. You have the host, that is not a domain or a fully qualified domain name, but it's an IP address, also very suspicious. And then that's it, right? You have the ELF here. So I would say this is very suspicious, yeah. Is it common to send binary files with a content time text plain character UTF-8? That's the question, right? So when you say send, you mean the internet to you, right? Because the red is what the client is sending. See here, right? Red is client, server is blue. So the server is sending you something. I will go with no, because this should be octet stream or should be binary or something. So that should also capture the attention of the suspicious. Thank you very much. Okay, then, yeah. Let me see. Oh, you mean the timing of this? Yeah, for sure. So it's a good point. Let me find out how I did that before with, oh, there. It's a good point. I would say, let me repeat that. Is something suspicious with the timing, right? Like you start the computer and then very fast you download something. I will go with it's not. But it depends a lot, right? So maybe it's a router that is updating. Maybe it's an IoT device. They download a lot of stuff, right? So, and also when we start this capture, we didn't start with a computer booting like before. We started kind of in the middle, right? It's like the first packet. So we don't know. Maybe we capture this in the middle of the day, right? So in this one, I would say, I cannot say. If I see the computer booting up like we did before, then I'll say, oh yeah, right? You are booting up and then you're downloading an NTPD ELF file, because this is not a Debian package, right? This is a binary. So I would say that's probably suspicious, right? So if you continue with this, now we can also ignore this. You can also try to see everything that happened with that IP address in port 80 and HTTP. So if you put this new filter, you will actually find everything done by this computer. And now you have more things, right? So, oh, okay. So you did the get NTPD, but also you did the get SSHD, whatever that is, and then OpenSSH, which was okay, and then bash, and then TFTPD. So it's downloading many things or trying to download many things, which already gets very suspicious. You download like 5 files. I don't know what they are, but you don't use a domain, right? Same IP for everything, so very suspicious. I would say we have confirmations of some of the downloads. You can do also this to see only the downloads. So how do? We take a note and we say this was downloaded, screenshot, screenshot, screenshot. This is something that you will also have to do for the bonus and for the exam. When you are doing an analysis, you need to document the whole time. And that means usually a lot of screenshots because stuff changes and maybe you cannot do that again because, I don't know, the computer is down. So every time you have something that you need to report for a penetration test, for you, for an exam, for the bonus, screenshot and you annotate. Screenshot and you annotate. Packet numbers. The intention is that somebody else should be able to verify what you did, okay? Just don't go there and say, it's malicious. That's not gonna fly, okay? So, how do you forget it?
I want to add to that is that remember that if you tell someone, oh, this happened in packet 66, right? The person has to open the capture, look at the packet 66, and do the analysis again. So the point of you taking screenshots and putting everything in the document or report or whatever you do is that the other person can just look at what happened and not having to redo the analysis again. You don't want to pay 2 people to do the analysis all the time, right? Because analysis is expensive. A capture can have like 1 million packets. So whatever you put there, you need to make sure that someone doesn't need to open the capture just to understand what is going on, okay? Yes. You will remember this in Christmas.
So now we can forget it. So you copy the filter, you put it there, you press enter, bye-bye, we forget about that. So what's next? Not a rhetoric question. What's next? What is that? Come on, get into the minds of the packet analyzers, threat hunters, pen testers, threat intelligence engineers, all job positions. So, what is this? So, we have something sent to port 23, and port 23 is reserved for usually telnet, and you have it here in the bottom, right? Telnet. So this is a computer, the same computer, by the way, so also we confirm that there is one client, connecting to this same computer on port 23, and again, it seems that there are some problems. Retransmission, 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 sending the scene again, retransmission, 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 sending the scene again, and look at the streams, right? Like 9 and 11 and 12. So, how do we do here? We can actually check all the traffic to this external server on port 23. So you can do this filter, the filter on the document, and now we have only port 23. And when you do that, you see that there is at least one of these connections that happen, and it's real, and it's there, right? It's from the TCP, got the CNAC, and then something sent in this protocol. So right-click, follow TCP stream, and you see this. So what is that? Text. What is that? So we have read, which means the client sent bildungs, whatever that means. Maybe it's a specific language that I don't know. And then in blue, the server answer, exclamation mark, star, scanner on, and then on red, the client sends proving. How does it look like? What does it in your mind? What is like? I'm getting commands, right? So I'm communicating, bildungs, I will take it like, hi, how are you? And then, or I'm alive. And then somebody sending you looks like an order, scanner on. And then you're saying, yeah, okay, I'm proving. This is a very much confirmation that that looks like a command and control channel. This is like, oh, you are sending things and you are doing it to me. Do you remember when we were doing like the light Hydra and sending commands and receiving commands? They look very similar, right? That is a confirmation of a command and control channel. So that is specifically, I'm going to close this, one of the connections. If you keep looking here, I'm saying that stream number 9 was the first one. So I'm going to go back to the previous filter. When you see all the telnets, stream number 9 was the first one, but then we have 11, and then we have 12, and then we have 13. That is the one that it was working, right? So that's very nice. This is stream number 9. So you can continue looking at all of these ones, right? And then you have stream number 10, and until you find the one working, that in this case is 13, okay? Stream number 13. So we are ready to take this out. So we saw that it's telnet, we saw that it acts as a command and control server, no problem. So if you keep looking at the streams, do you notice something suspicious in destinations IPs? So keep looking at the streams. It means after this telnet, you have stuff. Do you find anything suspicious there? What is the suspiciousness? And just it's a simple enumeration going from up, right? And just incrementing. And it's incrementing in a weird way. So who scans like this? 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3 is like very weird, right? I'm not sure if it's on purpose or it was a bug. I don't know. So it's actually connecting to many computers on the internet, one by one, incrementing, all of them port 23. Why is doing this, do you think? And benign or malicious? Benign, malicious, benign. Middle, you don't know. Could be malicious, why? So, scanning ports, we have many ways of scanning ports, right? Remember this, horizontal scan and vertical scan. Vertical scan, one computer, all the ports. This is horizontal, one port, many computers, right? So you just go. There is no reason to do this type of scans kind of in an official way, let's say. It's very, very suspicious. A vertical scan can be the administrator checking what ports are open in the router. A horizontal port scan like this is like, whoa, yeah, that's probably suspicious. And also the way that you realize the IPs are being created are very weird, right? And the fact that it's searching for telnet, also suspicious because we know many malware that is trying to find telnets open so they can actually connect, like IoT devices. Yes, they are open, many of these ones with 23. So when you look at this is almost malicious. I would say, again, a confirmation, right? But if you pay attention, yeah, this is like all the telnets and you see what's going on, right? And actually, if you want, you can search all the ports with 23, with TCP port 23, those are the same, and you see all of them, right? And some of them are retransmissions, and then some of them are packet syncs. So how do you know which ones actually found the computer open? Well, you can filter with which ones have a length of the packet more than 0, because in here, you only have the computer trying to connect, but there is nothing back. So when you filter and say, I want to know in the TCP level, TCP, not the whole packet, TCP, which ones have more than 0 bytes, you have only the previous stream number 13, which confirms only one of these ones was working, and it was to get answers from the command and control. So I conclude that none of the scans that we saw before, I will select the previous filter, these ones, 23, none of these ones actually was successful without going through all of them. I checked that there are no packets in those, data in those, okay? So at the end, we have this big filter. This is the last one that when you put this filter, you see all these packets, and oh, and something is wrong. Oh, I I make a mistake in the filter. Huh, that was weird. Let me see if I do this, and then I also do not port 23. I will go with this one. Let me see if I can fix it. And not port 23. I will copy the new one. Sorry, I mess up. I don't know why this was not working. Oh, there you go. So that is the last filter, and means that there are no more packets. Pa-bam! You end up the analysis. Okay? So this is the way that you can actually check which of these packets are malicious or benign. We went through them, and we identify by hand a command and control channel by looking at the content. Okay? Questions? No questions? Was it easy? Was it hard? Did you do it? Of course, are many options around. Yeah. When I replace this one? No. This one? Up, up, up. Yes. More, more, more. Yeah. Oh, this one. Oh, thank you very much. So yeah, I think it was this, but without this one, right? Oh, thank you very much. I will go. Yeah, thank you. We'll see later. Okay, questions? Yeah. Good point. So when you look at this, yes, thank you very much. You were asking, like, when you're looking at this, if that computer, the client, was the command and control channel, it was the server, or connecting to the server. So who wants to answer this one? Was it the server? Was it the client? What it was doing? Who wants to answer? Exactly. So you have like, oh, I'm connecting to some computer, downloading an order, telling me to scan. First, sorry, I'm going to some computer, downloading binaries. I don't know what happened, but it looks like the binaries got executed because you see connecting to 23 as a command and control channel, getting an order telling you to scan, and then you see a scan going on. So that confirms you are the client, somebody is the server, and whatever is that computer is infected. What you should do, at least right now, go and block it, power off, reset, reinstall, or something, okay? Should you be worried that other computers in your network are being infected? Well, not from this capture. No other computer in the local network was contacted, no other order was received about this, right? So you can be sure of how to approach the situation, right? Okay? Super. So let's move forward. So to recap, oh no, we have analysis summary, yes. So the capture contains traffic of a host, that computer, which seems to be infected with malware. We identify the following key behaviors. That's a benign device, doing management traffic on port 22, a benign DNS traffic, benign ARP, benign NTP traffic, and malicious that you have suspicious connections to a server unavailable, malicious file downloads, malicious telnet as a command and control, and network service discovery, okay? That would be a fast summary of what happened in this capture. Okay? So to recap, malware analysis is very important as a skill. I suggest that you practice a lot. Even if later you use tools, tools are awesome, but you need to use the tools, and you need to know what the tool is doing, and most importantly, what the tool is not doing, okay? So it's very hard to learn. There are many things going on, but this is the deepest you can go packet by packet, okay? So malware attacks can be found like this. So be very methodological and take notes. Don't try to jump stuff that you don't know, but that's when you're going to miss something, okay? So that being said, now we did the manual analysis. This is super awesome. I like it, but it's a little bit tough. If you have a lot of packets, that's not going to be easy. So what can we do? What we can do are network flows, and that's why we are going to be analyzing traffic with Zeek. So What is Zeek and what are NetFlow flows? Who can tell me what is a network flow? What is a network flow? But you did have networking the class, I know. So, and your teacher maybe is watching right now, saying, I thought that. All the, what do you say, all the packets? Yeah. All the communication between the two same endpoints and ports. And what else you say? Same IP, same port, there you go. So yes, something like that, right? Like everything getting together can be considered flow. So let's go into it. Zeek, in this case, formerly called Bro, not anymore, it's a network monitor tool that quietly and unobtrusively observes network traffic and interprets what it sees to create compact, high-fidelity transaction logs and file content, officially taken from the Zeek documentation. So it's a tool that allows you to create flows from the network traffic. And what is a flow? Well, this is an example of how to create a flow. In the middle, you have packets. This is packets like in Wireshark, like in TCP dump, okay? So if you look at these packets, you have some time, and then you have some IPs, and then you have source ports and destination ports, and then you have flags and scenes and synax and everything, and then you have more things. By the way, pay attention here, small thing. Usually the people says, oh, the destination port is 80, then that is an HTTP connection. It's not really true. When you look at this packet, the source port is 49,170 and the destination port is 80. But when you look at the second packet, the source port is 80 and the destination port is 49,170. So actually, what's a source port and what's a destination port? Well, it changes in every packet. To simplify, we take the destination port as whatever you wanted to connect. So this 80, okay? But technically speaking, if you say, print me the source port, well, it's going to print 49,000, 80, 49,000, 49,000, okay? Got you? So when you take all these packets together, a flow is an aggregation, is an idea of summarization. A flow is a conceptual idea represented by text, only text with ASCII, okay? So this one here is the flow. So you have one flow that is this line, and this line is a combination of fields and packets. So the first one is the TS. The TS is the timestamp, is the time of the first packet in this series. So how do you know from all the packets in the network which ones are actually together? Like Lucas was saying, the combination is like this. All the packets that share a source IP, a source port, a destination IP, a destination port, a protocol inside a time window are considered part of the same flow, okay? You have 5 values, tuple, 5 tuple plus a window of time. Inside that, you are considered the same flow. So all of these ones are considered packets belonging to one flow. So flows allow you to forget all those packets, plus the content, plus everything. That's too expensive. And just keep this ASCII representation. So TS is the timestamp, that is in seconds. Then you have the source IP, source port, destination IP, destination port. And then, sorry, the protocol, the duration. How do you compute the duration? There is no duration in the packets, right? So how do you do duration? First to last. Last packet minus the time of the first packet. What happens if you have only one packet? How do you compute the duration? 0 duration, right? That's good. You can say, hey, 0 durations. By the way, this is not simple. There are many standards of network flows, from NetFlow to IPFix and others. Each one is taking a different decision. Like, for example, having a dash instead of a 0 for no duration, whatever. The duration is here is time of the last packet minus time of the first packet. bytes sent by the origin, the source IP, the bytes sent by the response, or that is the destination IP, the state of the connection, packets sent by the origin, packets sent by the response, and you can have more. Okay, everybody? What's a flow? Yes? Okay, so let's start using flows. Yes. We have now using Zeek. So please go to your CTU Docker, and online people go to your SCL class 11 lab Docker that you should have started. So if you go to the Cyber Lab, there you go. You should have your class number 11. And when you click in the class number 11, you should have everything you need. You start the Docker, and then you are going to be inside. However, pay attention that in the document, internet, we said that you should be in the class 11 Docker, not in your hacker lab. So that's because you need to log in, remember, to the Docker of each class, something that Martin started to do like 2-3 classes ago. So here there are the instructions. You SSH with root, that is my current user, 272.20.101, and the password. Oh, I think I should start it again. Yeah, because I reconnected, stop and start. There you go. I try to connect. Do you trust you? Yes. The password is admin. And now I'm in the class 11 lab. Okay, internet? I will give you 20 seconds to get there. You should do the class from that Docker. That's why in the document you have the, from now on, SCL class 11 Docker. Okay, everybody? CTU, are you in your Dockers? Then let's go and get into your main root folder or home folder. If you only do CD, it's going to take you to your home folder. That's why it's there. Then we are going to create a folder called Zeek logs, right? There you go. Yeah, already exists. So let me delete it. Zeek logs. Okay. The same here. I'm going to create that. Oh, already have it? No. Perfect. And then get in there. Okay, all of you. No, get in there. And now that you're in there, let's execute Zeek. That's the command. -C, which means if the checksum of the pickup is bad, try to fix it and continue, because some packets can be cut in the middle, which is very bad. So C is fixing that, and R is read this file, okay? So you execute that command, and then you should have files in the same folder. Please, all of you, be sure you have files in the same folder, and those are the flows. So, technically speaking, the flows, as in the protocol specified by IPFix, it's only the con.log file. But Zeek is interpreting protocol. It's very good at interpreting and finding which protocol is those packets. So it's creating flows interpretations or summary data for all the protocols that could find, like DNS, files, HTTP, NTP, and others, okay? So let's go and see what's going on in here. So if you cannot do this, there are backups logs in here for CVUT or here online. If for some reason of the world you cannot execute Zeek, then download the log, please, and analyze with us. So we already saw what's in there. I'm just going to do it here. Oh yeah, I did run it here. I'm going to run in the Cyber Lab. So you see it running there. And now I'm going to see the content. There you go, the same content. Now, you can open these files. I'm going to use less, sorry, so you can see the content. I'm going to make this larger so you can see. And here you have flows. So if you pay attention, Zeek is adding a lot of headers. That's with a sharp sign. And it's telling you, okay, the separator I'm going to be using to separate the columns is the hexadecimal 09. That is a tab. It's a tab, okay? So between columns, there are no spaces, only one tab, okay? And that's because when you are taking information, when you're taking data from the network traffic, possibly controlled by an attacker, there are going to be text like the HTTP domain, stuff like that. And of course, the attacker can put there spaces or commas or anything. So it's a bad idea to use as a column separator any character that the attacker can introduce. That's why this is not a CVE. It's more like a TSV, like tab separated values, okay? So it's very hard for an attacker to actually inject a tab. That's why we use tab for column separation, okay? And then we have, yeah, set separations are the comma, empty field is gonna show as empty, the field that is not set is gonna be like the dash, the path for this of the file is called con, it's open in this moment in time, and these are the fields. First field is TS, that is a timestamp. Second field is UID, that is a unique random ID generated by Zeek for this run, specifically this run. And then ID origin host, that is the next one. And then ID origin port, that's the next one. As you can see, there are not aligned the fields, which is very annoying. And that's why we are going to be using a command called column. So if you do the column command, you will see now that we can align the name of the field with the content of the field, which is much better. So if you can, it's better to, to do column, and now you can very nicely see which is what. And then you have the type of field. So the first field is time, and the next is a string, and like that, and like that. The problem is that the first column, that is time, appears here because they put a column called field, so it's very hard to do that. But you know what I mean, okay? So let's take a look at these ones. We have the ID, and now we have the port, and I'm pressing the right arrow for going to the right. We have a destination port, 80, and then we have TCP, and then the protocol that is not there because there is no upper protocol, and then we have the duration, 3 seconds, origin bytes, response byte, connection state, S0, we are going to be looking at this later, local origin, local response. So if the origin is local, which means a local IP, yes, true. If the response, the destination IP, is local private computer, it's not. How many bytes were missed, 0, the history, origin packets, and more and more and more, okay? Pay attention, we are going to be using these fields for everything today, including machine learning, okay? So try to see what we are looking. And of course, you can go down, and you can see very fast everything that happened. 80, 80, 80, 253s that are DNS, I can go to the right, and then we have another 80, and then NTPs, 80 NTPs, right? And then you have more NTPs, we have the first HTTP here, and then more and more and more, until all the things that you were doing with 80, that's download, 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 more download, like we don't know, but there are TCPs, right? And if you go down, 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 you will see all the scans too, right? Oh, sorry. Scans, 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 scans. Which means that you can have a fewer amount of lines to analyze almost the same content, okay? Questions in flows so far? No? So, let's try to see a little bit more about this. The other flow log that is very nice is DNS. So let's see DNS. I'm going to be using also Zeekcat, because Zeekcat kind of gets all those headers out and gives me the correct header on top. So look at this. If I do Zeekcat, actually I have the TS on top of the TS. Oh, so thank you very much, Zeekcat. And also, if you pay attention, is transferring the Unix epoch time, that was a long integer or float, into the real human time date. So that's very nicer to see which one it is. In the DNS flow, if you look at the DNS flow, you will find information about DNS, like, oh, okay, that is a port, that's a protocol, that's a transaction ID, that's the RTT, and that's a query. Oh, it was a Debian pool 0 something. And also you have the query type, the query name, and then you have even the answers. Okay, look at this. We have answers in here. So everything regarding DNS is interpreted, and you can very nicely analyze this without the need to filter or nothing. Say, oh, all those DNS were done in the capture. Nothing weird, very fast, we go up and down. Okay, DNS log. Let's look at the files log. So if you go to the files log, you will see fewer amount. So we have now also the TS. We have the UID, but also we have something called file UID. the files have their special random UID, so they can tie together. The UID is crazy good because you can have one UID and then search in all the files for that UID, and then you will see how they tie together, the connection, the HTTP, the file, and maybe something more. So in this case, those are any files ever downloaded that Zeek can identify. And you can see here, they were downloaded using HTTP, the depth, the analyzers, the meme type, executable, no file name when they were downloaded, the duration, if it was local or not, the SYM bytes, total bytes, overflow bytes, timeout, extracted, SHA, everything, okay? So you know that 1, 2, 3, 4, 5 files were downloading using HTTP, and something was downloaded there, okay? Files information. Then we can do the HTTP one. So HTTP is the interpretation of the HTTP protocol. It's going to be very similar to the files because here only HTTP was used for files, but you can see now the names of the files. So it's downloading the URL and the version and the user agent and the Linux GNU something and the body and the response, if a user or password was used, nothing in this case, and exactly which files corresponds to these ones, and they were executable. So a very nice summary. It looks so easy, right? It looks like simple because Zeek was doing everything for us. And then we have the NTP log, right? This is benign, remember, we already saw, but you can see the IPs, destinations, and the port 123, and a lot of information about the version mode, precision, and everything. So, very fast, I want to tell you about the reference ID column. Do you find anything weird about that reference ID? And what is that reference ID? This one here, right? Reference ID. This is NTP, Network Time Protocol, synchronization of time between computers on the internet. You are downloading the correct time. So this reference ID is a reference of who is the service, computer, something, clock, that is telling that server to tell you the correct time. So those computers usually are very large computers with atomic clocks on the world. There are many of these ones, but very nicely you have GPS. So here it's telling you, oh yeah, the time I'm giving you, I got it from a GPS satellite, right? So you can see where the time of your computer is coming from, which is very nice, I have to say. So that's because Zeek can interpret the protocol. So after that, we wanted to go into the state. If you remember when we were doing the conn log, so go back and do the cut of the conn log there, so you see the main file, you will see that one of the columns, one of the fields, one of the features was called conn state. And conn state has many values, and this is a very important field. So let's go into this one. The conn state identifies the final state of the connection and can be one of these values. It can be SF for any connection that was established and terminated. This is your traditional connection in TCP. I start and I finish. S0 means, oh, you attempt to connect, but no replay come back. These are all the zeros that you see here, right? Some of them are SF, which means there is established connection. Some of them are S0. And then you have S1, S2, S3, originators and a sink followed by a thing, no SYNAC from the responder. You have responder send and reset, connection established, the originator aborted, connection attempt reject, and many others, okay? So looking at the state, you have a very clear idea of, did the connection establish? Are we sending packets? Or this is just, you know, an attempt like a port scan. Very important for taking decisions. The other field that we want to analyze is the one called history. History is a concatenation of all the TCP flags used during the connection. So instead of giving you the final one like SF, the connection was established and finished, there are many ways to establish and finish a connection. So the history is telling you all the bits inside those flags. So this is an example of a connection. Imagine, right, this is a flow, a time, or something more, and the connection is this one. So how do you interpret that history of the flags? And these are the letters. That means when you see an uppercase letter, it means that it was sent by the source IP, origin. When you see a lowercase letter, it means it was sent by the responder, the destination IP. A SYN means the traditional SYN-ACK, SYN without the ACK. H means a SYN-ACK. A is a pure ACK. D is data, F, fin, and like that, okay? So here you can say, oh, the origin sent the SYN, then the destination sent the SYN-ACK, and then, get out of here. And then the origin sent the final ACK, then data was transferred, then the destination sent more ACKs, and then more data sent by the destination, and then the T, which means in here the retransmit packet, retransmission, fin. You see the history, okay? Yes? So, you can go and check the rest. There is no problem. The very important one before the break is that this symbol, the hat, means a flip connection. This is crazy important because it means that for reasons, maybe because you lost packet, because your network is not very fast, whatever, some of the packets were lost, which means that maybe if the first packet was lost, what you think is the source IP is not really source IP, maybe it's the destination IP. Because imagine that A connects to B, and then B has to say, oh yeah, SYN-ACK, I want to connect with you. If you lose the first packet, you just see as a first B connecting to A. And many computers and many flows generators will say, oh, computer B is the originator, is the source IP. Well, it's not, you just lost packets. So if Zeek find out that packets were lost, it's going to tell you, hey, this connection is flipped, which means you have to actually flip the source IP and destination IP, okay? It's not going to be done for you. Okay, questions before the break? No? Okay, super. Let's go to the break. We have 10 minutes, is 36. We are back at 46, okay? Internet, we are back in 10 minutes. Go get a media luna, put a toast, some butter, or noodles if it's night for you, or morning. Okay, let's continue, people. We are late. You didn't tell me, you sneakies. Sneakies. So let's just jump 3 pages. No. So, example of a threat hunting question. So this is for you people. For you have some minutes. You need to find the following. With whom did the client connect? Okay? So we want to find out the destination's IPs and ports of all the hosts with which the client has had established connections. But we only want those that transfer data, okay? So take a moment, think about the problem. Yes, the solution is there. Take a moment, think about it. We are going to be doing a lot of this now in the bonus, in the exam, like finding information, threat hunting, asking questions, who connected, to whom, when, why, how often, okay? So try to make this happen. I'm going to give you a couple of minutes. How would you find this? for you. We have to find the destination IPs and ports of all the hosts with which the client had established connections transferring data. So, how you doing, internet? Yeah, everybody. Everybody. Okay, I'm gonna take a look. Okay, if you didn't solve it, you can also try later, but you can do it in many ways, including Wireshark probably. But in these flows, I'm gonna cut them. Okay, let's make it happen first. You copy this, you go to wherever the logs are, and in this way we can find the IP addresses and the ports of all the computers that we connected and we transfer data, which is MTP, NTP, NTP, DNS 180 and 123, which matches actually what we found before. So how do we do it? Well, we do the cut of all the flows, and then we use awk, remember this amazing programming language, and we are splitting the columns by tab, so because this is a tab separated file, and then we actually make a small script here in Violet. And the script says, well, if the third column is the IP of the client, and if the 12th column is S1, remember the established connections we saw before, or double pipe, the 12th column, that is the state, is S2 or S3 or STO or STTR or SF. All that means established connections, okay? So if it's coming from the client and the connection is established, and the column number 10, that is the data transfer, is more than 0, then print all the columns. $0 means all the columns, which is the flow. And then we are just gonna split again by tabs, also getting the column number 5, a space, and column number 6, that is destination IP and port, and then we sort, find unique values, and we sort the resulting unique values, okay? Was it clear? Was it too much? What we like about these one-liners is that you can script very much, you can put in Splunk or Kibana or anything like that, and you don't have to have a huge program doing that. Of course, you can do this in Python or something, but this is usually much, much faster, including, especially if you have here like 10 million flows, okay? So, let's now do a small thing about extracting files. And extracting files is a very special feature because Zeek, apart from being Zeek, has extensive language by putting new features as scripts. And the language is Lua. So you can program in Lua something very complicated or very whatever you want, and then you can create a package for Zeek, and then you can execute it. So in this way, you can go and check all the scripts there. There are many doing a amount of weird things. We are going to be using one called extractallfiles.zeek. So if you run this Zeek command again, in these Zeek logs, if you run this Zeek command again, I'm going to run in every part, then you should have a new folder called extract files. So what this is doing, it's going to every flow and trying to see if there is a file, and if there is a file, is getting all the bytes and then creating the original file. So if you go into the extract files and you list, all those 4 are actually the real files transferred in the HTTP. So you get them out of the pickup. And you can actually see that this is true, because if you do file, which is a command to see what type of files are those files, I know, complicated, then you will see that says, yeah, this is an elf, this is an elf, this is an elf, this is an elf. So completely extracted the files. Be careful, don't execute, this is real malware, okay? That being said, do you see now why it downloaded 4? Do you see why 4 downloads and not only 1? The answer is there, out there. And the answer is that they were from different architectures. Ah, sorry, I didn't see you. If you are going to say that, yeah, very good. I will give you that one. So MIPS, Renesas, and x86 and ARM. So it's downloading one binary per type of architecture because IoT, and then it's just executing everything. It's gonna work somehow. Okay. So that is the analysis, and if you can actually want to see the commands that are supposed to be executed by the malware, you can do reverse engineering like you did here in the previous classes, but also you can do strings because these commands are open strings on those files, and when you do that, you will see exactly the commands inside these binaries, okay? So there you go, cd, tmp, cd, bar, run, command, and then you can see that it was trying very specifically to do very executions, parts, anonymous, FTP gets, and many other things, and then deleting everything, right? So you have here a very nice real malware pipeline of execution of how to infect a machine, okay? Very nice to have. You can print a t-shirt with that one. Okay, so as a recap, flows are critically important in most organizations because organizations cannot keep pickups. That's very, very expensive. You cannot have pickups for 20 years. You don't have space. This is like hundreds, thousands of terabytes. But you can have flows very, very cheaply. So it's easy to store, very easy to use for detection, and you can import in many, many CMs, okay? Questions before going to the next one? No questions? Yes, questions? You sure? Okay. Now for the automatic detection of command and control channels and attacks with machine learning, what we're going to be doing there is showing an alternative way to analyze traffic automatically. I know that most of you may not be familiar with machine learning, so who is familiar with machine learning? There you go, machine learning, something. You hear about machine learning. You know somebody that knows machine learning. I'm trying to find some connection here. Okay, so don't worry, we are going to be very slow, but I have to say that if you go into security, well, if you go into most fields IT, at some moment you are going to be hitting something with machine learning because it's getting better and better and better. It's helping automate many things from reversing to attacking to spam filtering to network administration. You are going to be hitting something or a tool or something doing machine learning. So let's go and find what we can do with machine learning. For that, we are going to be using a Google Colab. If you don't know, this is kind of a Jupyter notebook in Google for free. And for this, you need to use your Google account. I'm sorry, but there is no way around this. We are going to be accessing, this
Sorry,
is the...
Can you explain for those that do not know what a Jupyter notebook is?
Yes, a Jupyter notebook is a special type of web document where you have Python code that you can run kind of line by line, and you can also print and plot in the same web page, and you can annotate. So it's kind of a very slowly and coordinated Python execution, and it's crazy good for machine learning, data analysis, and stuff like that. And Google has one of those called Google Colab in this link in here that you need to access. It's going to ask you to actually log in with your Google account, so please log in with some account. We don't have a way around that for all the people in the internet, okay?
And it's important to know that what you run there is not running on your computer. It's running on Google's computers, okay? So whatever crazy machine learning, very expensive process that you run, it will run on the cloud. So you can have like a very basic computer, but then you can run very expensive processes in there.
So when you get into this Colab, please make a copy so you can execute, because if you don't do a copy, you cannot execute the lines, okay? Go there, file, save a copy in Drive, and then you open that one, okay? So I'm gonna go to my copy. This is mine, class, oh, this is actually class 11. Okay, I will change later. Manual attack detection, and we can start, okay? I will give you some seconds to go there. Be sure you have a copy. Internet, please, make a copy. No question from the internet? Are you okay, internet? Are you shy today? Okay? So, automatic detection of malicious traffic with machine learning. Our goal is to analyze these Zeek flows. We are going to take the Zeek flows because they are text, and we are going to start trying to analyze the data, filter the data, clean the data, plot the data, understanding the data, and then build a machine learning model that we can actually execute and try to find out the command and control channels. Remember, this is very, very hard. The amount of command and control channels are very few here, so we are going to be doing an effort to make this happen with such a small amount of data, okay? So we are going to start there, importing Zeek, exploring, cleaning, building, testing, and something for later, okay? So, how do you work with Google Colab? If you click with your mouse, you will see that you have different type of fields. Some of these ones are actually text, so if you double click, you will see that this is Markdown, and you have like a small editor here, okay? The way you execute each of these cells is with Shift-Enter. If you click Shift-Enter, the cell is going to be executed. If this is Python, executes Python. If this is Markdown, it's going to be doing this interpretation, okay? So see, this is Markdown, I click Shift-Enter, and it's converted back into nice text, okay? And if you keep clicking Shift-Enter, goes to the one below, so you can click Shift-Enter again, and stuff like that. So, first, we are going to install things, because this is a computer that Google is giving to you for free. So you have to install everything you need. And that's done by the !pip. So go to the cell and press Shift-Enter, and you will see that you are actually downloading things and installing, okay? So press Shift-Enter, pip install umap learn, import umap. As you see, we can slowly work with the Python. You don't have to do everything together. So you just import it, then we will use it later. Now we are going to install ZAT. ZAT is a small library. Actually, we are not using this one. It doesn't matter. But it's a nice library for analyzing the Zeek into pandas. So you press Shift-Enter, and we are going to be installing ZAT. Okay? In all your computers. I'm going slowly, so you have time for installing. It's going to take like half minute, okay? Then we are going to be installing the Pandas library. Pandas library is a very specific library for easing the analysis of data for data analysis and machine learning. That means that it's allowing you to prepare the data, clean the data, explore the data. So instead of having a list like in Python, you have a very special list that you can have columns and indexes and stuff like that is called a data frame. And then you have ways of cutting the data frame and like doing kind of SQL things on the data frame. Very, very, very fast if you want to work with machine learning. So we do like import pandas as PD, Shift-Enter, be sure that you are clicking Shift-Enter in all the Python code. Then we are going to be using NumPy. NumPy is a numeric library. Actually, it's one of the most efficient ways to deal with numbers in Python. If you have a lot of numbers and you have to compute things, I suggest you use everything with NumPy. So if you create a NumPy array, it's going to be crazy fast behind the scenes, okay? Then we are going to be installing matplotlib. This is a library for plotting things like curves and stuff like that. Shift-Enter in there. Then we are going to be installing sklearn. Sklearn is a library for machine learning. Basic machine learning is called it, where we are going to be using a clustering algorithm and some scalar algorithm, okay? So you do Shift-Enter, and we are going to import sklearn. Then we are going to be using the library called IP address, because we are going to be converting some of the IP addresses. So Shift-Enter, import. And in particular, the data table is a structure created by Google for specifically the Colab, and we are going to be using this one because it's very nice, and we have some parameters in here. So Shift-Enter, and that's it. Some of the new things that Google put in the Colab, and actually are quite good, is that if you are in any of these Python codes, you have here some icons, and the third one now is Gemini. So when you click that, you have an AI that you can explain the code. So if at any moment later you are lost, you can click explain the code, and it's going to go to this Python, and it's going to try to tell you what's going on in here, okay? Yeah, I don't know what. Oh, because I was choosing the E here, sorry. So actually it's very good. And then you can say to the AI, hey, can you solve this problem or something, improve it, font, whatever, it's gonna work, okay? So in summary, Pandas is data manipulations, sklearn is machine learning, UMAP we are going to be using for dimensionality reduction, I will tell you what is this later, TensorFlow we don't have here, but it's a comprehensive machine learning library, Keras is a more high-level library for machine learning, and Matplotlib for data visualization, okay?
Can we just pause for 15 seconds?
Yes.
Is everyone there? Like internet as well? Tell us. I feel we are going pretty fast, but if it's okay, you can tell us. It's fine.
Perfect.
Yeah.
So now we need to download some data, and there is something called a file conlog label that is on the internet that you don't have to download to your computer, only in Colab. Everything happens in Colab. So this code here is gonna go to this website, that is our website, the Malware Capture Facility Project, and it's gonna download the file. You can change this for any file you want, and then it's gonna just get it in this computer. So when you execute this, it's gonna be downloading a file, and it's gonna be keeping here. If you click on the left where you have files, you will see that the file now is kind of in this computer that you have on the web, okay? So you just download it once. That's why the if in there. And if you do commands like ls, you will see that, yeah, actually you have the file in there and some other things, okay? It's like managing a remote computer. Then we are going to be importing the data and cleaning, okay? So I already told you about Pandas data frame. That is a very fancy table, a very fancy matrix that you can put names to the columns and you can move the columns very easily. So we are going to create a data frame by loading the flows file from Zeek. So Zeek has columns with times and IP addresses. We are going to create kind of a matrix in Python that with the log2df create data frame. So if you execute this, that file is going to be converted into a data frame called the conDF, connection data frame, okay? And now the information is the same, but it's interpreted, and you have all the columns and all the types of data. So if you do len of conD, like conDF, like in Python, you will see the length, that is 7,000 lines, okay? Everybody, be sure you can do this. If you just put the name of a variable in Colab and you press enter, it's going to show you this variable. In this case, it's a data frame. So this data frame is interpreted. This is the Colab tables, and you can actually see here the columns, TS, UID, origin, right? And see scrolling to the right, scrolling to the left. Very easy to see all the data. Very easy. You can even sort here by things. You can click. You can do stuff. It's kind of interactive, okay? So this is your main data frame with all the information that you have from the Zeek logs. Now that we have this data frame, we want to know what type of columns we have. That's done by the types. Dataframe.dtype, like any Python object. And it's going to tell you, oh, the column UID is an object. The source IP is an object. The source port is actually an integer 64-bit. So it's trying to interpret. This is a number, you are a float. This is a number, you are an integer. I don't know what you are, you're going to be an object, okay? So you have different types of columns in here. If we do the dataframe.describe, including all the columns, you will actually have a summary statistics of each column. So here you have the UID, or the origin source IP, or the source port, and then you have the amount of rows that have a value, 7,000, and then you have how many are unique, the top, the frequency, the mean value, that's the average port, the standard deviation, the minimum, first quartile, second, third, max. So there's a little bit of analysis of each of the columns for you to see. So when you are a data engineer or a data science engineer, you look at this searching for patterns, anomalies, is everything fine? Do we have an issue with the standard deviation, right? What's going on? Something I didn't tell you is that we have two new columns in this one. One is called label, that we have malicious and benign. And the other was the detail label, where we have things like part of a horizontal port scan, or command and control, right? So these two labels were put by humans. So in this one, we have labels because we need to use it to train something and later to validate that we are doing this correctly. So we need labels here, okay? Next, we can, well, actually see the labels. So see, I'm doing the data frame dot label. That is the column. This is a way of choosing a column in a data frame. And then unique is counting unique values. So when you execute this, you say, oh yeah, the unique values are benign and malicious. That's it, okay? If you do the same for the column detail label, you're gonna see that has actually more. None, some of them are empty, not a value. Some of them are part of a horizontal port scan. Some of them are command and control. And all of them are of type object, okay? Questions? Small stop? Internet? Okay, let's continue. Now, because some of the columns we don't need for what we are going to be doing, it's a very smart thing to delete everything you don't need because you don't have memory for this. So here we say, oh, look at this. Get the data frame and just drop the columns that have these names, tunnel parents and UID, because we don't need those. And once you do that and you drop the columns, store these in the same variable, in the same data frame. So I'm kind of replacing the data frame with a better data frame. Other thing that you can do is that you can use these brackets to actually search for specific rows, 100 to 110 in this case, so you can analyze and see the data as much as you want, okay? And see all the values that are in here, right? See here, benign, malicious, benign, malicious, benign, malicious, none, 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 part of a port scan, okay? So the data analysis here is very, very nice. Then we have the exploratory data analysis. We are gonna be plotting things. So the first plot we are going to be doing, we are going to be creating a plot with some parameters for the font. And in this data frame, connection data frame, we are going to be using a very special operation called group by. Group by is creating groups by some criteria. So it's like you have the whole data frame, but I want you to separate rows based, in this case, on the label. So now we are going to have a structure that everything that has the same label is going to be together, and you can reference that. So in this case is, okay, look, separate everything by label, and then take the column called label and just count how many of those columns labels are in these groups separated by label. We are counting how many flows we have per label. And then we are going to be creating a plot, dot plot. See how kind of easy it is? You have like a column, and then you do dot plot. And that's it. Pandas is plotting this for you. So in a way, it's helping a lot do this analysis much faster, okay? And then you can say, okay, create a plot, dot plot, and then do a bar horizontal. So I can use the type of plot, bar horizontal, and then the size figure. And I can even put titles, right? So if you access the plot variable directly, you can actually change it. So I'm going to execute this. And look at that. Okay, maybe a little bit too big. There you go. So you have horizontal bars with the label malicious and the label benign, automatically counting how many of those are here, like 3,000 and 4,000 and something. Okay, everybody? Now you have an idea of the balance of labels and how this is working. Now, let's plot the same, but for the detail label. So we are doing the same group by, but by the detail label. And when we plot this, I'm going to plot it. And then if you pay attention, there is a very specific but important parameter in the plot called log x true. That means the scale of the x-axis should be logarithmic, okay? Logarithmic. That's why you see here that flows having the label, the detail label command and control are in the order of, this is 10, right? This is 100, this is thousands. So 10, I don't know what is this, like a 6 or something like that. And in here you have like thousands, and then 2,000, 3,000, something like 4,000, okay? Logarithmic scale. Logarithmic scale because they are so out of scale that if you don't use logarithmic, you just don't see the columns, okay? But actually, I want to know the numbers. So you can do the data frame, group by, okay, group by, the detail label, and then specifically you get the detail label and you just count. So when you execute this one, it's telling you, oh yeah, command and control, there are 8, and part of a horizontal port scan is 4,000. So this is what we need to detect later. All the benigns, all the part of a port scan, but specifically the command and control, okay? Small stop, questions? Internet questions? How's your data exploration going? Data scientists? Okay, so now we want to plot the sent bytes by the origin, source port, and the received bytes by the destination, okay? So how do we do that? This is a little bit more complex. We are going to be creating from the data frame, extracting the column origin IP bytes. We are going to be doing drop na. Drop na means if in this column origin IP bytes, there are any values that do not have a value, I don't know how to say, like, doesn't have a value, just drop them, ignore them. We don't want to give empty things to the plot because it's going to fail. And then we just create a plot, dot plot, okay? So the first line creates a plot. But instead of plotting the plot or showing the plot, we store in a variable called axis, which means now we can do things with this plot. In particular, we are going to be getting a grid of the y, that it means like the vertical axis. And the third line, look at this. We are going to get the information from the data frame, but now the response IB bytes, the bytes coming in the opposite direction, also dropping, and we create another plot. So this line officially gets 2 plots together in the same axis. 2 plots together in the same axis. And then we have some ticks for the fonts and adding the legend. At the end, we have one graph with 2 different signals. We have in blue, whatever it was sent by the origin, in yellow, orange, what it was sent by the destination. Do you see some patterns in there? Anything that is telling you about what you should be looking at? You are the defender, you are the analyst, threat hunter. You need to be taking decisions out of this. Internet. What do you see? So in particular, there are some large amount of horizontal values, but you have some peaks. And peaks, these are bytes being transferred, so flows that are transferred more. So this is a situation that we are sending something, but the orange is a situation that we are receiving something, and we have 2 of these ones. So maybe the files that we're downloading, right? We were downloading some executable files, and then some of the things that they are sending, maybe NTP, sometimes the orders, we don't know. But here we have flows that we can later check what they are, okay? Important things to verify. Remember, you are trying to separate automatically the command and control channels. Then we are going to be doing something that is called resetting the index. That's why, because before the timestamp, the TS, it was taken as the index of this table. Imagine an index like a database. But that's not a good idea because the TS, it's actually a value. So by doing and executing the reset index, what you do is creating a really new numeric index with 0s and 1s and 2s and 3s and 4s and 5s. This one here now is the ID of each flow, and the TS happens to be just a column, okay? So we are kind of cleaning more and more and more. Now we go into some of the columns that we know, like TS, and we want to do some transformation. Why we want to do this? Because if you have something that looks like a number, I need it to be recognized as a number. Like pandas, NumPy should say, this is a number. So the algorithms know later that this is not a letter. It's not a letter in ASCII 2. It's actually the number 2. So they can do operations like minus and plus and executions. So here we are going to say, look, the TS, that is the timestamp, reinterpret as type float. The label is going to be a category, which means can only take specific values. That's a categorical variable. Only specific values, like command and control or benign, okay? The detail label is also going to be a category. The protocol is also going to be a category, and the state is also going to be a category. A category is a very specific type of variable that you can actually operate on. So remember to execute it, okay? Next, we are going to be actually changing the integer that was the source IP to the real object of an IP address. And this is done by the library IP address. So we are going to take this that used to be a string of ASCII letters, or used to be even a number, and we say, no, 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 this is going to be an object, and the object is going to be the IP address object, and you can do many operations on this. So if you execute this, now pay attention that I'm replacing columns, okay? Data frame, this column, now is going to be the same column plus an operation. The operation is similar to the lambda operations in Python. I'm not going to go to Python, but apply a lambda function with the integer, okay? This means that right now the int is going to take the object, that is the IP address, and it's going to convert into the integer representation. Remember that IP addresses are just bits, and you can look at that as 4 octets, or you can take the 32 bits and convert into an integer. It doesn't matter, okay? So here we are converting into integers. And now that we have the columns in roughly the way we want, we can do a very special operation called the correlation. And for that, I'm introducing a new library called Zeborn. Zeborn is another library like matplotlib. And what we are going to be doing is we are going to be taking the data frame, selecting only the numbers, because we cannot do that with something that is not a number. So we have a new data frame called numeric. And then we use the operation heatmap in here. So when you execute this one, heatmap, you're going to see the heatmap. And in a heatmap, let me make this smaller. There you go. You have horizontally all the features, all the columns, TS, source IP, destination IP, and the same columns horizontally, okay? Vertically, sorry, the columns, horizontally the same columns. And now, every time 2 of these columns, imagine here we have origin packets, and here we have TS. If you pay attention, there is a small number in each of these intersections. And the numbers that corresponds to this scale here goes from -1, that is black, to +1, that is white. And that means the correlation. If you remember, the correlation means if 2 values are growing together, positive correlation, or they are decreasing together, negative correlation. They can also be doing like this. One grows and the other one don't grows, okay? So positive correlation, sorry, and if they grow in the opposite sides, negative correlation, okay? Let me say that again. Grow together, decrease together, positive correlation. They grow up and down, decrease up and down, negative correlation. And if they have nothing one to do with the other, right, if they move differently, you have close to 0. So here, what you are looking at is, oh, actually, when something like the origin host changes, what's going on with the time? And the correlation is 0, which means nothing. There is nothing that is tying these values together. But, for example, you can see that the response IP bytes, the bytes IP sensed by the response, and the response packets are very much positive correlated, which makes sense. More packets, more bytes. Less packets, less bytes. Okay? So this is a way of very roughly analyzing how are your features working together. And why we are doing this? Because if 2 features are very high correlated, you can delete one, because it means that they are not adding any value. If they grow together and decrease together, I don't care. Why I do have to analyze both? So you can delete one, and then you have less data, which is awesome, okay? So this is a correlation analysis. Now that we have the correlations analysis done, let me increase this. We are going to pre-process some of the data. So what does it mean, pre-processing? Well, it means that, for example, some of the columns are empty, or they have errors, right? Somebody was typing and make a mistake. So you can actually use this knowledge and start deleting columns, start deleting rows. Maybe you need to do some transformations, cleaning the data. If this sounds too much for you, let me tell you sorry, let me tell you that in machine learning and data analysis, 80% of the time is only cleaning and getting good data. Then doing the model is kind of like model. But the trick is not so much the model, it's like getting the data correctly, okay? And this is gonna be one of the issues for you. So let's change the flows without label. So, hey, do we have flows that don't have a label? Pfft, maybe we do. I don't need those. No label, you're out of here. So we have the data frame, detail label, data frame, detail label. The category we are going to add is the category, we are going to be adding a new category called dash. And then we are going to say, hey, look, if the detail label, fill it, all the NAS, fill all the NAS, fill all the empties with the category dash. That means I don't want empties here. I just want categories. Or you have a label, or you have a dash, okay? That's what's happening in this line. Then I can show you how the data frame looks so far. So I'm gonna describe it again. And so, oh, look, we have TSs, and we have now, look at the numbers, right? The numbers in here. Oh, disconnected the runtime. Damn, that's bad. Okay, we'll see. Are you back, runtime? Oof, yeah. And then we have ports, so similar as before, but we are cleaning more and more the features. Then we are going to create a new data frame only with the numerical values. I'm going to forget everything that is not a number, like the state, right? I don't want those. So I'm going to create a new data frame called numdf. That data frame is going to select all the types that are a number. See? All the types that are a number are going to be here. And then we are going to be adding the state from the other data frame. We are going to be adding the protocol column from the other data set, and we are going to have the source IP. So here what I'm doing is kind of selecting. I want a new data frame called numdf with all the numbers plus source IP plus protocol plus state. Okay, we are going to be working with this one. And you can take a look at how does it look. And also you confirm that you did everything correctly. Okay, numdf. Please run it in your collabs. I know that it's easier to look at me here, but be sure that you click on this and runs, okay? After that, we are going to be discarding more columns that we don't need. For example, I don't want the local origin, I don't want the local response, I don't want the service. Delete all these columns. They are too much data for me. So there you go. Again, press enter, delete the columns. We describe again, just to be sure everything works, is good. Yeah, we have less columns. Let's keep moving. Now, I want to analyze any other column. Do they have values that are not a number, are nuns? Do they have anyone here that still has not a number? And for that, you can do, okay, that's the num data frame, dot is an A, any is an NA, any is not a number. And when you run this, actually you find that yes, duration still has values that are not a number, origin bytes still has values that are not a number, and response bytes still have values that are not a number. I don't know, maybe ICMPs, I have no idea. So we need to solve these ones. How do we solve these ones? Well, if you want to know which ones are there, you can just print them. Data frame, origin byte, whatever is an A, print it. So you just execute that, and it's going to print it. And you can see here, right? Durations and origin bytes. So I don't know, some of the flows, maybe because they don't have many packets, I'm not sure, they just got none values. So the way of solving this is not straightforward, because if a flow does not have a duration, what are you going to do? First option, you delete the flow. Bad idea, because you're going to lose data. Another idea is to replace the values with something, but replace with what? So the idea here is like, okay, look, if you have a flow that doesn't have a value in the origin bytes, it's because it didn't send bytes. So I'm going to fill all the empties with zeros. The same with the response and same with the durations. If you don't have a value, I want a 0 there. And now we kind of recover, okay? So now we have zeros. I'm going to check that it's fine by printing if duration has na. Duration does not have na, we clean the duration. Now we are in a very particular situation that the dataset is clean. Finally, it took us like 25 minutes, maybe half an hour, and we need to work with categorical values. So imagine this. You have dogs and cats and fish like the column animal, okay? How can you work with this? How can you train a neural network with something that says dog? Very tough. This is not a number. You cannot do is dog less than cat, right? Of course it's not. But I mean, you cannot do that. So what you do is a technique called one-hot encoding. What hot encoding means? I will take this column with values, cat, dog, fish, and for each of these values, I'm going to create a column. And then for each row, I'm going to say, do you have that value, 1, or you don't have that value, 0. That's why the transformation created a column fish, cat, and dog, and then you have, you don't have, you don't have, you have, you don't have, you have, you don't have, you don't have, you don't have, you have. This is one of the critical things why neural networks work. Without this, no neural network can really work well. So first, I'm going to print the protocol, and it says, oh yeah, we have UDP, TCP, and ICMP. What about the state? I'm going to print the state. Oh yeah, we have many states. So that's bad. Let's create the one-hot encodings. That is the pandas get dummies. It doesn't matter why it's called the get dummies. It's called get dummies. But when you execute the get dummies, automatically converts all these categories into the ones and zeros. And you can find it here that if you scroll to the right, you will find a new column called constate OTH, constate reg, constate const, protocol ICMP, protocol TCP, protocol UDP, and then files true, okay? Do you see? We convert these into ones and zeros. Everybody? Small stop for questions. Internet? No questions? One hot. What? Yeah. Such a good question. You deserve a Mando. There you go, Mando. What you? Ah, well done. That catching. So the question was, what's the benefit, right? Like we can convert dog and cat and fish into numbers, like 1, 2, and 3. Of course, cats are 1. And then it's like, what is this better than that? And the question is that if you do that, then the algorithm will learn, oh, 1 is actually less than 2. And then when you go to your data, it means cat is less than dog, which doesn't make any sense. Or green is less than red. Green is not less than red. But if you convert it into numbers, some algorithms can make differences. And then you have very bad situations. So to avoid that, you convert into columns, and then you are training the algorithm, or you do have this, or you don't. But you cannot say that is more or less than other category, okay? This is a very old technique.
Can I add one more thing? Yeah. Another advantage of this is that the distance, when you're measuring distance between the two values, is always the same. Whereas if you convert to numbers, then like if you were subtracting, for instance, 3 and 1, it would be like different than the other categories. So this is creating a little bit more columns. But when we are scaling and when we are like comparing the distances, which is something that a lot of the algorithms is doing, this is beneficial and more robust for later on for the training.
Was it clear? It was not on the screen, but it was on there. Okay. Yeah. So the thing is that this is an old technique because now we have embeddings and we have transformers and LLM. So I know, but this is another way of looking at kind of an embedding space of this, if you know what an embedding space is. So now that we have this, we can print the columns. So numDF, we have some columns in here. Pay attention that now it's called numDF2, the one with the hot encoding. And you can actually get the values. So remember, numDF is a data frame, very fancy, very expensive, with names and columns. We don't need that for making numeric operations. We don't want the name of the column. So what usually is done is you take the values inside this nice database, and you just create a Python matrix with the numbers. That's what the value Nasdarabi is doing, okay? df getting the values, and we will call this traditionally X. This is the data set we are going to be using for training the models. And when you execute that, also you can see the shape of X, shape of the matrix. So it's like 7,800 rows and 22 columns, okay? If you are curious and you want to know how does it look, X, you execute this command, and that is your X, okay? Numbers and truths and falses. Now, feature scaling. Why we need to do feature scaling, and what is feature scaling? Feature scaling means taking columns with values and making sure that all your columns that have numerical values are in the same range. So ports go from, which is the smallest port you can have, port number? 0. And which is the highest port number? Very nice. So that is a range. But if I ask you the IP addresses, when you convert IP addresses to numbers, well, it's much more. You can go from 1111 converted to decimals, to integers, to several trillions. So what you need is to have all these features in the same range. Can be from 0 to 1, -1 to 1, I don't care. But you need to scale them, because if not, again, like Ondra was saying, every algorithm that is searching for larger, every algorithm that is searching for bigger is going to say 3 millions is more than 10. That's easy, right? But that's bad, because you don't care about that. You care about the relationship. So that is called scaling. And there are many methods for scaling. I'm going to be using one that is called the standard scaling or standardization or Z-score, which is basically taking each number, that's the X, that's the X, taking out the average and then divided by the variance. And that is scaling everything, okay? So we are going to take the standard scalar, that's the object, and then we are going to fit. Fit in this context means to train, to create this scalar that is empty, and to modify the scalar by fitting it to the data. X is the data, fitting the scalar to the data. That is the training process. And now that we have this scalar, we can use the scalar to transform that data. First, you learn, fit, and then you transform the data. And now we have something called scale data, okay? Now that the data is scaled and we are working with the scale data, we are finally going into some machine learning algorithm. Oof, that was tough, but we are here, okay? You ready for the first one? Questions? No? Do you feel the data science getting into you? Okay, the first, no, yes, go data science, go. So, the first one that we are going to be using is called clustering. What is clustering? What is clustering? I'm hitting the mando. Oh, so generic, you are a good data scientist. You say nothing and you say everything is good. So a group of techniques that kind of, again, cluster, the clustering clusters the data according to some technique or idea. You create groups. Yeah, go, I'm repeating. It's close together in some sense. That's good enough. There you go, your second mando. You can start selling them. Oh, she took it. Oh, no. Oh, the mando is okay. He can fly, or she can fly too. Yes, clustering is any way of finding, we say, the natural way the data gets or relates together in their natural groups. So if you look at something and you can find ways that this is actually naturally getting together, those are clusters. There are many clustering techniques. We are going to be using one that is called DBScan and is using the Euclidean distance. if you remember Euclidean distance, Pythagoras, like kind of this Pythagoras in here. So it's taking 2 points, making the distance, and using this distance to start searching for ideas, okay? This is an example of clusters with different colors. Oh, 1, 2, 3, 4, 5, okay? Many methods. The one we are going to be using is called dbScan, and it's called like that because it's based on density. What is density? Well, density is the following. If you look at this graph, every point that you have, you get who is close to you, okay? So if you have many of your friends together in this circle that we call epsilon, all of those that are close to you in this epsilon are called the core nodes, the red ones. You are the core, you're in the center. If you can only have one friend, like the yellow ones, that you are in the border of this core, you are one of these border nodes. And any point that it's not connecting with anybody, right, like the blue one here, you see, is called a noise point, anomaly, failure, or something. So dbScan is a very well-known technique that is getting together things by density. We are going to be trying to use this one, okay? So no need to execute that. How to use dbScan? We need to set up two values, the epsilon and the minimum amount of samples. We are going to be putting some in here. You can play later. So go to this line that says clustering dbScan, epsilon 5 means samples 20, number of jobs 1, and fit. Remember, fit means training. Train, learn from this data, learn a clustering. So you execute that. You get the clustering object. It's going to take some seconds. Clustering. Now is the machine learning magic happening behind the scenes, and we have a clustering. If you get to this object clustering, you can find the labels. The labels are the numbers of the clusters. So execute that for the first 100 points, and you can see the first point is in cluster 0. The second point is in cluster 0, 0, 0, 0, 0, 0, 0. Oh, there is a point in cluster -1. There is a point in cluster 1. There is a point in cluster 2. Okay? Got the idea? Internet? No questions? Weird. Now that you have idea of what the cluster did, you can find how many clusters do we have? Well, that is how many unique labels we have. We have a cluster -1, cluster 0, 1, 2, and 3. Okay? We have 5 clusters, and you can find the 5 by using the length of the data right. That is a fine. Now we can actually print each of the columns that were used. So we have the columns in our data frame, and we can kind of assign an ID. So I'm going to say, okay, if you're the first column, I want the ID 0, 1, 2, 3, okay, it says IDs of columns. Okay, everybody? And why we are doing that? Because I want to plot now. I want to plot these columns once against the other. I want to analyze. I want to verify what the clusters look like, what's going on in here. So I'm not gonna go into this Python. You can actually explain with Gemini. That is very good. But what this code is doing is literally going one by one each column and creating variations, and according to the type of point, getting one of the graphs. So here, for example, it's I'm plotting the origin host, which is the source IP, that's the Y, against the origin port, right? That is the X. And as you can see, it's bad. I mean, it's not useful. I cannot understand that. It's like just some points, some are core, some are red, some is like, okay, clustering, that's did not help at all. That means that for analyzing the clusters, like the clusters are assigned, it doesn't mean that you can look at them or you can visualize them, but we want to visualize them. So we are going to jump into a technique, very nice, very modern, very much used, called UMAP. And UMAP is a dimensionality reduction technique. What does it mean?
Sebastian?
Yeah, sorry.
We should go to a break.
Wait, what? Are you sure?
Yeah.
Okay. So let's go into the break, and then we continue with UMAP, people. 10 minutes, 54, we are back. Okay, let's continue, people. Internet? Come back from bathroom or wherever you are. Let's continue. Let's data analysis. Let's machine learning, people. We left our machine learning unattended. That was bad. So, ready? How is that data science? Do you want to change from cybersecurity to data science now? Do you want to jump into AI? Who is here in the AI track? We have the AI, data science. Who is the AI people here? You don't want to appear. You don't want to say, yes, I'm in the AI, data. It's okay. Oh, you have some people there. I just noticed. See? So that's why you choose the path of data science and AI. So, dimensionality reduction, what is this? Dimensionality reduction is a group of techniques where we have a data set, we have a lot of features, columns, like 20, 30, 40, 100, 1,000. This is too much. Imagine the people doing science in biology, that they have like DNA, that have thousands and thousands of features. How do you work with that? Well, no, super tough. So, one way of doing this is to try to reduce the dimensions from 40 to 5 or to 3 or to 2, right? So literally, you are taking data, and then, in the case of UMAP, you are trying to find how these points are topologically related, and then you extract this topology as a graph, and then you try to map in a lower space of dimensions respecting the features of the topology, which means whatever was closer in the high dimension should be closer in the low dimension, just something like that. So this is a group of very powerful techniques for visualizations, for clustering, for analysis. Without this, a lot of things we cannot understand. So let's gonna use UMAP to actually found relationships in our data. There are two main parameters: the number of neighbors that you are gonna be using and the minimum distance, okay? So again, if you go to this Python cell, you have an object that is gonna be called reducer, that in the object library UMAP, we are gonna be UMAP with these numbers of neighbors and distance, and then again, we fit transfer this, which means training and transforming in the scale data. So scale data is going to be the input. It's going to take like a minute. It's going to be the input, and then this input is going to be analyzed. It's going to be transformed into specific type of graph, topology one, and then searching the dimensions until having these embeddings. And then we are going to be printing the embedding shape that is 7,000 to 2. We went down to 2 dimensions. So now that we have these 2 dimensions, we are going to confirm from the original data frame the unique labels we have. So we have the detail label nothing, part of a horizontal port scan, and CNC, okay? So first, we are going to be using UMAP, this dimensionality reduction in 2 dimensions, only with the real detail labels. No clusters here, no DBScan, only the real labels, okay? So this is a very small Python that we are assigning colors. So the no label is going to be black, the command and control is going to be red, and part of a horizontal port scan is going to be blue. And then we create a figure, and we do a scatter plot. Scatter plot is like only points in X and Y. No columns, no lines, just points. That's a scatter plot. The embedding is the output of the UMAP. So embedding is going to be the first column, that's 0, and then second column, that's the 1. We assign the colors, some transparency, and we just plot, and that's it. So this is a scatter plot of how it looks to have UMAP doing this transformation. This is your whole data set in 2 dimensions, and as you can see, there are topological differences. Like kind of these groups are together, all these blacky things, all these blobs we have here. And if you remember the labels, we had black, it was no label, which usually is benign. no detail label, it's benign. Remember, you have benign malicious and detail label, nothing, port scan, command and control. So all these blacks are usually the benign ones. Then we have blue, the port scan, and red, the command and control. So you see the port scan is quite different. Port scan is different, very easy to detect. But now, look at the command and control. It's literally borderline in the corner of the benign. It's like, oh, shoot, like, yeah, we have the labels, but we are going to have some issues understanding and identifying those. They are going to be tough ones, okay? They are not like a blob like these ones. They are kind of mixed with the benign. Okay, everybody? Understood UMAP? So, now that we have an idea in this new dimensionality space of what we need to search, let's add the clusters. What does it mean, the cluster? Well, we are going to have the same blobs, but the colors, instead of being the actual labels, the colors are going to be the clusters found by our dbScan cluster, okay? So we are going to be the similar colors as before, but now the colors are the cluster. -1 blue, 0 red, 1 green, 2 yellow, 3 magenta, and then we just assign the colors based on the clustering labels. See? Clustering labels. One small detail here. If you remember the clusters found by dbScan, 3, 2, 1, and 0, those are, I will call, the normal clusters. But if you remember, with the core points and everything, there was a group of points called the noisy points that are always assigned to the cluster -1. So -1 are kind of the weird, right? The outliers, yeah. So going back here, you can see the same plot as before. I mean, the blobs are the same, but now the colors are the clusters. And that means everything red, what is red? The cluster 0 is what dbScan said, yeah, all of these look similar. And if you remember the original labels, these are the benigns, okay? Let me go up a little bit, see? Benigns. However, the port scans were also mixed in these benigns. For dbScan, benign and port scans were kind of close together, okay? And then we have other cluster in green, number 1, that for some reason is here, you see it here. And that was also benign. So there is a different benign according to dbScan. And then the yellow is cluster number 2. This one's here. That is the yellows, okay? And according to the labels, those were also benigns. So this is another type of benign. And then the magenta is the 3. That is, I think, here, a little bit here, and also here, right? Those are, again, a different type of port scan. So kind of some port scans are related. But very nicely, also, you have in blue here, the -1s. So these ones, if you remember, were the command and controls we were searching for. And the blue are also here. That means that dbScan was actually quite good. Created one cluster in blue for all our command and controls, and then they were also related to some of these ones here, I think benigns. That's a confirmation that the clustering kind of worked. It was enough to find out that these command and controls were different from the rest in a way, okay? Ah, sorry.
A question from the internet.
Yes.
How about UMAP followed by HDBScan? First UMAP and then...
So remember that dbScan and UMAP, it's not that there is one after the other like in a chain, right? So we first found clusters. Those are theoretical, not theoretical clusters, it's like numerical clusters, right? You find the features and then you say cluster 1, 2, 3, 4, 5, okay? Then UMAP is a way of visualizing this in a lower reduced dimension space. So UMAP you can do without clustering, and clustering you can do without UMAP. It doesn't matter. We are mixing so you can see visually that actually these blobs are similarly separated by dbScan. There is a little bit of a bias because technically speaking, UMAP is also a little bit of clustering. So the way UMAP works is also searching for a little bit of differences. But if you pay attention to the blobs, when I'm saying the blobs are the points, for UMAP, these blue points and these red points are not different. If we don't put colors, you will never find those, okay? In the case of this blob, UMAP says, oh yeah, this blob is different from this one. So the clustering, blue and red, was able to separate the command and controls. UMAP, this blob in here and the blob here, was not able to separate the command and controls. Was it clear? So it doesn't matter the order. UMAP now is only visualization. DBScan is the real technique that learned the shape of the data. Yes.
Now I hope, oh yeah. Yes, but you could theoretically use UMAP to reduce the dimensionality of the data, so from 11 features to 3, and then do some algorithm. And this may actually sometimes work better, because basically you project to another space, and yeah. So in theory, internet, yes, you could do both, but you may lose some information. So
yeah, true story. So if you first use UMAP, as Mari says, you already gain a knowledge. You separate blobs. So a lot of techniques are first you mapping, and then doing something on top of that, and actually works quite well. So after this, if you do an analysis of these clusters, okay, analysis of these clusters, that means, okay, now we have clusters. What's in these clusters? Okay, let me stop a little bit here to see if there are questions. UMAP, DBScan.
We have another question from the
Yes.
internet about when you do the conDF label unique and you call that, and it gives you benign and malicious.
Yeah,
This
okay.
is assigning the labels or retrieving the labels.
So when you do that, conDF, and then you have the labels and then unique, and then you count, what you are doing is getting the original column feature of the label that says malicious, 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 benign, 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 malicious, malicious, benign, no, and then you find the unique ones, which is malicious and benign, and then you just count like 2 or 3. It depends on how many of those you have, okay? So I want to know if, I think I did it back. So here, for example, I was doing, okay, get the labels of the clusters. That's literally 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 0, 0, 0, 1, 1, 1, stuff like that. And then you just find how many are uniques. That's this one here. -1, 0, 1, 2, and 3 are unique values, so no repetitions. And then you count the length of this array. So this array, how many positions it has? 1, 2, 3, 4, 5. That's why there are 5 unique clusters, okay? Getting from the label. So here we are not assigning, if I understood your question correctly. If not, please ask us again, okay? Okay, now that we are after these clusters, we were here, here, here. Okay, so how can we see what's in the clusters? And for that, what we do is getting the original data frame, and we are going to be grouping by the tail label, okay? Remember the tail label like command and control, stuff like that. And then we are going to be counting. So this is only counting how many we have in total, no clustering or anything. We say, okay, command and controls, 8 flows. That's not a lot, okay? Part of a horizontal port scan, 4,000. Without the detail level, 3,000. These are the benign, okay? And now, to see what's in the cluster -1, we do, okay, look, data frame. Get all the values where clustering labels is equal to 1. So clustering labels equal, sorry, to -1. Clustering labels equal to -1. That is an array of position. Remember, what's inside clustering labels? 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 2, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 0. That's clustering labels. When these are equal to -1, that is put in true. So now you have an array saying false, 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 true, 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 false, 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 true, 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 okay? That's clustering levels equal -1. But because the order is the same order and is in your conDF, what you are doing is conDF, you are gonna select the rows where this is true. So you are literally selecting the rows where the label in the clustering was -1. Okay? Got you there? A little bit tricky, but works. And then once you select the flows that have the clustering level -1, we are going to group them by detail level and we are going to count. So when you press enter, it's going to say, oh, in the cluster -1, you have 8 flows that says command and control, 4 flows that says part of the horizontal port scan, and 16 that are benign. That's pretty good. We have a cluster that has all the command and control, only 4 port scans, and 16 benigns. We are fine. We had like thousands, okay? Is it perfect? No. Can it be perfect? I don't know. Maybe, probably not. So this is a very nice clustering of command and control channels. And then what's in the cluster? Okay, yeah, actually, I want to see the flows in that group. So you do the same, you select -1, but now you can do like head, which means the top of the data frame, right? So when you do that, then you're going to say, okay, those are the flows in this cluster. And you can see the IP addresses, you can see the ports, you can see the protocols, you can see the durations, and you can see the labels at the end. So the last, these ones here, were all command and controls, okay? See? All command and controls. Got you? Work for you? Perfect. Be sure that you execute this. You're going to be needed later. Believe me. Now, what's about in cluster 0, right? Okay, let me see how many things we have in cluster 0. Same as before. Okay, we don't have any command and control. We have mostly part of the horizontal port scan and a lot of benign. Why they are these together? Pfft, I have no idea. So let's see. Show me something in this cluster. And I said, well, a lot of 23s, right? The part of Honda port scan, a lot of benign. I'm not sure why they were clustered together. I believe that we can improve these clusters. Of course, if you change the clustering parameters, you're going to have clusters that are more pure, but you're going to have more clusters. So you're going to end up with 100 clusters. So maybe it's too much, okay? You need to balance the trade-off. So what about cluster number 1? Okay, let's see cluster number 1. No, get out of here. Cluster number 1. And cluster number 1 has only benigns. Okay, that's good. Can you show me which benigns? Yeah. Oh, look at this. All the NTP. Ah, that's nice. So all the NTP were clustered together. That's good. What about cluster number 2? There you go. Has what many? 152 benigns. Okay, which are the benigns? Let's see. Oh, ICMPs. All the ICMPs were clustered together. That's nice. Cluster number 3, the same. And what do you have in here? Oh, what do you have? Yeah, 41 scans and 6 benign. So the majority were part of the horizontal port scan, some of them benign. I don't know, maybe the duration was similar. Yeah, right, yeah, the connection state is rejected, right? So maybe they were rejected, I don't know, amount of bytes. I have no idea. We need some explainability maybe. So, what else can we do here? We are going to stop with this, but well, you can check the noisy and incorrect clusterings, improve the features, add new features from the other logs, add more data, try other algorithms, and many, many, many things. Yeah. So we have here the noisy ones, right, and many other things. So, as a takeaway, have a clear goal for your analysis. You cannot just do everything, right? If not, you're going to be lost. Be careful in your data processing. It's 90% of your results. If you don't do the cleaning correctly, you are going to have shit. Remember, shit in, shit out, okay? Always analyze the data and see if it makes sense. And the only way to deal with large amount of data and fast is this one. If you have 20 million rows, good luck with Wireshark, okay? So, questions before ending the machine learning part? No questions? Was it nice? Did you like it? No? A little bit? It's a nice automation, and you run Python, and it's finding automatically. And then you can run this in a new capture that you don't know and find the command and controls that are very similar automatically. And then you go create a startup. You're famous. Then you conquer the world. That's like the 4 steps, right? That's it. World domination. Okay? Ready? No questions? Internet? Yes, yes, no, no. So, now that we have this manual analysis of command and control channels, automatic analysis, a little bit with machine learning. Yes, go internet.
How can I validate the model with files or logs?
Good question. How you can validate the model? That's a very tough one, I would say. Of course, what we did here is like a kind of a toy example. If you want to slowly go into more realistic production, you would have issues like verification. So I would say the first thing you need is a good data set that you have labels. So if you have a good data set, which means a lot of benign, with variability, a lot of malicious of what you want to detect, and you have labels, then you're in a good position. Because then you can split the data set in training, validation, and testing, right? And then you training the training. You split a little bit of this for actually doing the validation. So you validate which of your models is best. And based on the training and validation, you select, oh, the best parameters for DBScan are epsilon of 25 and minimal something something. When you take this decision, then for the first and unique time, you look into your test data to see how much you can generalize to unknown data. I say, well, in my test data, actually, I had like 82% precision, accuracy, F1 or something. And that's a little bit better. But then you have a new data set because traffic is coming tomorrow, which means that you have different data set. And then you are facing the problem of this concept drifting, right? Like the thing that you want to detect actually may be changing. Or maybe the benign you're trying to detect is maybe changing. So you need to adapt. What does it mean? Maybe you need to retrain. Maybe you need to forget. A deep amount and a lot of topics. I'm gonna not jump here, but you have a lot of machine learning and AI things to get into. Very nice, if you ask me. Very beautiful. I hope it answered a little bit of the validation. Okay, are we ready for the last topic today? What we are gonna be ending the class with is a little bit of a system, an intrusion detection system that is actually already used in machine learning. So this is a way that they want to show you, okay, those techniques are very nice, but actually you can go and try to implement in real life with different results, maybe good, maybe bad, but going from this proof of concept into production, it's tough, okay? So that's what we are gonna be showing you, SLEEP's intrusion detection system. So SLEEP's is our own intrusion detection system that we create in the Stratosphere laboratory. Actually, Stratosphere Linux intrusion prevention system is the name. It's a Python-based machine learning tool. It's free software. You can go, download, you can contribute, make it better, and try. That is not relying on signatures like Suricata and others, but instead it's relying on the behavior of the connections. It's relying a little bit of how this looks like. What are they doing? How they are doing it, right? And in different ways. So you can actually go and check the code there if you want to download or use the Docker for your computer. The very general idea of how it works is that you have a lot of inputs, interface pickups, maybe Argos flows. These are flows, Zeek flows, folders, NFDump. And then all of these are parsed. We are extending Zeek with some scripts. And finally, this is creating a profile for each computer. So Sleep says, oh, you're a computer. I want to know everything you're doing, the whole profile. And these profiles are actually split in time windows. So you have everything that happened in the hour number 1, everything that happened in the hour number 2, 3rd, 4, 5, or whatever. We are storing everything in Redis, now also SQLite, and you have ways of consuming this. Calypso UI is a console-based UI. You have a web UI. You have many modules inside, logs, exporting, and everything. So I'm not going to go into each of these. Here is an idea of the things that it can do, from doing detection of IRP attacking, blocking in the Linux firewall, like doing trust models in peer-to-peer networks of sleeps detections, recursive neural networks for the command and control detection, asking virus total, doing a global peer-to-peer that is under construction now, and global trust model, creating a timeline, like updating threat intelligence file, many things, like detecting successful SSH even if it's encrypted and things like that. So all this is already installed in your container, so you don't have to install it, okay? But if you want to install, you can actually do these commands. Cloning, you only need the latest commit, and then you get in there and you can install with this command. You don't need that, but both in the Stratosphere Cyber Lab and in the CVUT Dockers is already running. So, oh yes, so it's time for maybe the password! Aha! Surprise! Ah, you thought I forgot about it? I did. So, data drop. That is the password. Data drop. Boop, 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 boop. Okay, let's continue. Now that you have Sleeps installed, let's make it happen. So, all of you, go to your Dockers. In CVUT is your CVUT Docker. In the Stratosphere Cyber Lab is your class Docker. So you should go here, okay? I'm gonna go there, okay? Everybody? Now, let's go into your Stratosphere Linux IPS folder that is in the root directory, like that. There you go. And let's verify that sleeps works. So you just do /sleeps-h to have the help. If it works, you should see the help. If you don't see the help, it didn't work. I will give you some seconds to be sure you have everything. We don't have time for explaining all of Sleeps. It's a complex piece of software. But if you like, go check the documentation. It has assembling of models. You can retrain. You can adapt to your local traffic. Very nice. Okay, everybody? And now we can actually execute it. We are going to be using a capture called training capture 009. This one is already in your data folders, both in the Stratosphere Cyber Lab and in CVUT. But if you want a copy, you can download from there. Maybe you want to check at home or something. So the first thing we are going to be doing is we are going to be changing the default threshold of detections of sleeps from the default that is 0.25 to 0.08. So let me explain this a little bit. When an intrusion detection system is detecting, in this case sleeps, you have two basic decisions. One is evidence of a port scan, evidence of an attack, evidence of maliciousness, evidence of something. Each of these evidences have how high is the threat level. Is high, medium, something. And then you have the confidence, how sure is Sleeps that this is really a port scan. And Sleeps will tell you, yeah, I'm like 75% sure, or I am 60, or I'm 100. So all these evidences are gathered together, and when you have enough evidence over a threshold, you generate an alert, and the alert is go block you. So you have an alert, and that means that it can go to the firewall and block, you can export, you can share in the peer-to-peer or something. That threshold has variability, and it's up to you. There is an optimum that is 0.25, but then you can go very sensitive or more conservative, okay? Here, because we don't have a lot of traffic, we don't have enough evidence because it's a short capture because of time. So we are going to change the threshold to the sensitive value, that is 0.08. which means we are kind of in an alert situation. This command, if you don't know Z or sed, it's a stream editor. Sed, stream editor, which means it's to edit, but line by line. So to sed, you give a file. This is the configuration files of sleeps, and this is the scripting. And the scripting is saying, search for, that's the S, search for everything that says column 025 and replace by 008. And do this in line. So this is a way to automatically change a file without opening the file or doing anything. It's a very nice way of modifying files. That's it. We modify a file following a pattern. Now we are going to go into our Tmax. So we have everything in Tmax. And now we are finally going to run sleeps. So you can execute this file, sleeps, and -F for the pickup. I'm going to be running this one. Oh, I didn't go into Stratosphere Linux IPS. There you go. And you should see, where am I? It's not in here? Oh, woo, what's going on? No, that's different. No, we should have it. Okay, give me a second. Let's try to download in the, I don't know what happened. Maybe, sorry? Yeah, the training capture 009 pickup is not in dash data, but it used to be. Can you check? Maybe I put it in a different place. So what we can do is we can download it from here. So let's actually go to the link I put in here, and I'm gonna download it. Don't do that. Let me just get the link first. It doesn't matter. Yes, just go there. And now I'm gonna go to my downloads. I'm gonna copy this link. And now let me see if I can get it here. wget that. Oh no, I need to do wget in command lines, in double quotes. Okay, so that's it. Are you done? Where are you? Where are you? Where are you? Give me a second, people. Where are you? Oh, it's here. Download something. Okay, so let me fix it. Yes, you are that one. I will call you. I think it's O test.pickup. Is it working like that? Oh, I think yes. Okay, so if you do this command, let me make it again here. And I'm gonna call this the training capture 9. Yeah, I'm gonna like that. Oh, yeah, there you go. And then I'm gonna change colors because I like my colors. If you do that command, people, sorry? Oh, pickup.pickup, yeah. If you do that command, you will download the pickup in your Dockers. Sorry about that. In the SCL, it was there in the Stratosphere Cyber so lucky internet worked for you. Now that you have this, I'm gonna do it again. Training capture 009. Oh, now it's in data already. So if you do the original command, also should work. So you should do also this and should work. Let's do it and see. Oh, there you go, found it. Thank you very much. So what's going on here? What's this doing? So sleeps, the version we are using is 1141. And again, remember that we are doing this because Alea was working a long time trying to fit sleeps in their very small Dockers. Sleeps has many libraries, and it was big Docker, and she managed to make this very small for us and testing for the whole week. So thank you very much, Alea, for your work. You can go and say hi to Alea in the matrix, and thank you. So what's going on here is that, let me go back. Oh, what did happen there? Oh, I press Control C in something. Let me depress Control C. I will run this again without my Control C. Storing sleeps logs, starting the modules, using Redis server. So sleeps is creating a Redis server, and in that ready server is storing everything, and then it's going to start different modules. In this case, you see that says starting ARP, flow, analysis, IP info, network discovery, risk IQ, command and control detection, threat intelligence, timelines, and others. So Sleeps start this parallel processes in memory. Oh, we have some byte. Wow, that was, what is going on? Alea, look, we have a bug to fix. Database manager is doing something. So let me show you here in the server lab that actually work. I'm gonna go up. I'm gonna go up. I'm gonna go up. I just want to show you how it starts. Oh, there you go. So starting modules, 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 modules. Each module is a process, okay? And these processes are working in parallel. There is a group of threat intelligence files. So Sleeps is downloading like more than 50 threat intelligence feeds from the internet, real ones. So, but these files take time. So what Sleeps is doing is like starting to download them in the background while starting to check the traffic. Okay, so this can take time because they are downloading in the background. They are loading memory, and the moment those are in memory, that's it. New times that Sleeps is running, they're going to be using these ones. So some modules in this case are disabled because you don't want all of them. And then you have evident process, profiler profiles, and then it's going to tell you, you don't see that in here, but it's going to tell you that, yeah, this is tough because it's in red and I cannot change this color. But it's tell you, hey, there is an alert, and the alert was detected because of the following evidence: unencrypted traffic, suspicious user agent, connections to unknown destination ports, another, okay? So there is one alert, then there is another alert a little bit later based on other evidence. We are gonna be looking at this, don't worry. And then you have, okay, I'm stopping, total lines red, that's the time it took, and now I'm stopping each of the modules. And if you pay attention, still it's working in my computer because it's saying, hey, look, some of the modules are still doing something. In this case, flow alerts, update manager, and evidence handler. If you want to stop Sleeps, just Control-C again, no issue. But if you let it go, it's gonna download everything, okay? In here, I'm not sure what happened. Did it work for you or also explode like me? Yeah.
Every Sleep instance creates the multi-threading, and we are like 40, 50 maybe people running Sleeps on the same server. So we have enough memory, but CPU is struggling.
Okay. So we have CPU issues. So if it fails for you like this, because, yeah, running 40 Sleeps, it's a little bit hard. Specifically because to be fast, Sleeps is multiprocessing, which means it's creating like 15 different processes. So let's wait a little bit, and then slowly you can start and click enter, or maybe after. So if you cannot see the logs, it's fine. We are ready for this. You should have the logs in output and some folder, but if you don't, there is a copy of the logs here. Data, Sleeps logs, training capture 009. So if it failed for you, don't worry. Go to the logs here, we can analyze together, and later you can run, okay? So Sleeps outputs many things, including to SysNet, including to emails. You can export in JSON, you can do many things, but in particular exports in text files, okay? So in this data, Sleeps logs, training caption 009, if you get in, you're gonna see files, alerts JSONs, alert logs, error logs, the SQLite database of all the flows, metadata about the capture, the whole output of the console, and a copy of the Zeek files. Because if you're running this in a pickup or in your own interface, well, you don't have Zeek files. So here you can have a copy of the Zeek files. So how we are going to be analyzing this? If you are using this data, Sleeps logs, I suggest you copy this to your own folder, output, okay? I'm gonna be copying this into output. And after copying, this is only if you don't have the Sleeps running, okay? If you do, should be.
Some of you, not all of you, but some of you at CTU may have some output folder from our testing yesterday. So if you look at the output of sleeps, there might be a folder from yesterday or the day before with some data.
You can use that, right? So everyone has some logs to look at? Yes? Yes? Internet? Yes, yes. So in the alerts.log, this is where you have actually all the logs of the alert. So I'm going to go to output, training capture 009, and I'm going to do a list of the alerts logs, and look at this. Okay. I'm going to press dash capital S, and you can say, oh, source IP something, sleeps works also with IPv6, and says detect connecting to a private IP. So this is because every time an IP address in the local network talks to another IP in the local network, it's telling you. If you go to the end of the log, to the right, you're going to see that the level is info. Info means this is not important. It's not counting to block you, but you should know about it, okay? And then you have other ones like detected, connected to private IP, suspicious user agent. The user agent is PV. That's suspicious. Unencrypted traffic. Again, is it bad unencrypted traffic? It's not completely, right? But you should know about it. It's level info, okay? And then you have enough to generate an alert. And then if you go, I'm going down, you have a connection without DNS resolution. That means you went directly to an IP address, but you didn't resolve a DNS name before, which is very weird. And you have detected domains that are resolved with no connection. That's the opposite. You did a DNS resolution and you never connected, right? And then you have more and more and more. There are too many. There are actually too many. Let's see how many. We have word count, alerts.log, and that is like 148. So how can we look at these ones in a better way? Well, you can actually cut this, and then you can get out of the detected column, and then you can just sort, unique, and sort again. So if you do that, you have a much better, I'm going to decrease the font so you can see, a much better, Tmax, a much better summary. So now you have a counting of, okay, you have 30 connecting to a private IP, 11 unencrypted, 6 private, 6 without DNS, 6, 6, 6, 5. You have suspicious user agent. You have, I'm going to go down. You have long connections. Look at this. Long connections that were 67 minutes, one connection, more than an hour. 67 minutes, 27 minutes. Connections to unknown destination ports, super important. Like you are connecting to ports we don't know, that's suspicious. Connecting to multiple ports. You are connecting to multiple ports in the same destination. Is it weird? Well, no if the port is 80 and 443, but yes if the port is 52,000 something. And actually we missed that in our analysis before, right? And look at this one. We have a device changing IP addresses. We have the IP address 130 using a MAC address, but now it belongs to 113. Yeah, okay, good to know. I mean, should not happen a lot, but maybe there is something going on there. So this script that I'm highlighting, actually we put in data sleeps alerts sort.sh. So if you execute that, it's exactly the same. And the last one I want to show you is a script that does the sorting but uses a command called watch, which actually checks continually the log file and updates. So if sleeps would be still running, you will see this changing in real time, okay? So you see the logs appearing and disappearing. So I'm going to stop this, I'm going to stop that, and I'm going to stop a little bit for questions. Questions? No? Was it clear? Yes, yes, no, no. What are we doing here? It's a lot, and it's weird to look at a complex program that fast without knowing what's going on behind the scenes. So go and try. You can use this to detect things going to your Dockers, to your computer, to whatever. But it's much better way to understanding the behavior in the traffic. And in here, you have at least 2 machine learning models, one doing command and control detection and one doing flow by flow a small neural network detecting, okay?
Remember that sometimes, I think we saw this in a couple of classes ago, that sometimes the goal of an analysis is to determine if a machine was infected or not, right? And we saw that, yes, we can look at all the packets and go super deep and check everything. But if the answer is yes, no, and we run an automated tool like this and give us an alert, and that alert shows that it's malware, then we are done, right? It doesn't mean that it will catch everything, but if it helps us save some time, well, the better we are for it. So if the tools, automated tools, do not show anything, then we can go and take the longer route and look at all the packets. Depends on the analysis, right?
And it's important to know how to do this by hand, because you need to check, is the tool good, is the tool bad? Suricata, Snort, this one, whatever you buy, right? How can you test, how you can evaluate, and this is crucial. And you will need different tools for doing your work, okay? No questions? Internet? Yeah. Yes. So the question is, if any of these tools are working in real time, this is a pickup. Yeah, this is a pickup. This can you also run directly in your interface. If you do -I, you put ATH0 and you read packets. So yes, can work real time. However, Sleeps is not meant for large networks. So Suricata, Snort are, Snort is dead, but Suricata, it's a very, very nice tool that it will detect attacks, but is mainly designed for attacks from the internet or from the outside to you, Nasdaravi, and then is designed for huge networks. So Suricata is optimized for gigabytes of bandwidth, right, and protecting the whole university, right? Sleeps is not meant for that. Sleeps is mainly meant for your computer or small networks, like 20, 30, 50 hosts, something like that. So up to that, it's fine. But if you have a lot of traffic, it's going to lag. So you're going to be doing real time, and it's fine. But then, imagine a port scan, right? You have a port scan happening. You see the packet. But when do you have a port scan? Is one packet a port scan? Well, probably not. 2 packets? No. 3? So you have to wait a little bit. So a lot of detections need some waiting. 20 packets, so you start to lag behind the real time, right? So the more traffic you have, the more Sleeps is going to take time to tell you something. So how much you need real time? Well, if you have an exploit or you have like an APT right now, probably you want to know as soon as possible. But a lot of attacks, you can wait like 5 minutes. It's like fine, like 10 minutes. Yeah, nobody's measuring how much time it happened from the real attack to the detection of the tool. It can be 10 minutes, it can be 5, it can be an hour, it can be half an hour, right? So it depends. Maybe half a day is too much, right? So yes, but be careful what traffic you have, right? Yeah. Another question? So we are not going to go into the web, but there is an extra if you want in here. Sleeps has a beta web interface, apart from exporting, like I told you before, that you execute when you do Sleeps with a -w parameter, or by executing the web interface shell script, and this is opening a web interface. Unfortunately, because we wanted the Sleeps version in the Stratosphere Cyberlab to be small, we didn't put the web in that version, because if not, you're going to downloading a huge Docker. But if you want, you can just go here and download the final Docker with everything, okay? Internet, maybe outside Stratosphere Cyberlab, like in your computers. The web is going to be open in this port 50,000, and if you can find with this is the way you can actually get into the web page, because remember that the web page is going to be open in your Docker. So how can you see from your browser the Docker in CVUT or in the Stratosphere Cyberlab? So remember that usually for this, we do the tunnel with SSH. So now your local browser can actually see a port inside your Docker. That's going to be the tunnel for here in CVUT. And if you are in the Stratosphere Cyberlab, you can do the tunnel with that. And then you just go to a browser with the web page that looks something like that, right? So it's a web page, and you have here the profiles and the computers and the alerts and more things and detections and more and more and more, okay? So we are not gonna be doing that now, but it's gonna be for you to see later if you want. So let's gonna stop here. We are ready for the assignment. You wanna go?
Okay, so the assignment for this week again opens at 9 p.m. tonight. We have a two-parter this week. So the first part is going to be some log analysis. There's going to be a pickup file. You need to download it. And there are going to be 3 questions that you need to answer. You have to figure out how you're going to analyze this file, use some techniques that we applied today. Some are going to be better for some questions, some not. So especially if you're playing for the Pioneer Prize, like knowing whether to use Wireshark or something else for that situation might be that like few seconds or minutes that will get you the prize, I guess. And yeah, then you answer the questions. And the part 2 is related to what we've been doing in the collab. So you will, again, you will see it in the CTFD. The collab that we've been working in today, you will need to modify something there and then answer the question. So that's it. Basically.
Questions? Assignment?
It's not too difficult this week. It's mostly some analysis, but you still need to be kind of in that mindset of how to analyze things and what to look for.
So a little bit of machine learning. Yeah. Interesting. So part 1, part 2, thank you very much. Also remember the feedback, important to us. Please, internet, go. It's like literally 10 seconds. Tell us some feedback, what you think, what happened, okay? So that's it, people. Thank you very much. See you next week. Get ready for Christmas. And bye-bye. Bye-bye, internet. See you.